Hello? Hello?
听得到吗？
Okay, welcome everyone for joining us today, and we'll be getting started in 10 minutes. Thank you.
对，看到我那边就是会录不起它。也还好啊，这边就只有87。不过印度他们因为会在哔哩哔哩那边录。不是，我想是排会。
Happening right now. Cambridge Forum Sounding G started at 9 a.m.
他那边容易控制的，没事，听他的呗。
但是底下是可以听的。
Okay, good morning, good afternoon, and good evening. Wherever you are in this world, we welcome you to the first Cambridge International Young Scientists Forum, the emerging technology for the next decade. My name is Zhuge Yunjian. I am a PhD student of chemical engineering at the University of Cambridge, and I'm also the vice president of the Cambridge Chinese Students and Scholars Association, and I will be your host today. Before we get started, I would like to sincerely express my gratitude to the following institutions and companies for making this event a reality. I would also like to thank the following student organizations for helping us advertise the event. The last 10 years have witnessed many scientific breakthroughs. The successful launch of the Curiosity rover to the Mars and discovering evidence of liquid water on the planet, the detection of Higgs boson, aka the God particle, the observation of gravitational waves for the first time, and the first image of a black hole, AI program beating human world champion of Go for the first time, the development of CRISPR technology enabling scientists to perform precise gene editing, and advancement of cancer immunotherapy, making us one step closer to curing cancers, just to name a few. Now, the real question becomes, what is the world would look like in 2030? I think it's only beyond our wildest imagination. However, we'll try to go there today. With the help of 22 top scientists in the field, we will try to take a peek of what science and technology will enable us to do in 10 years' time. It is very important for us young scientists and graduate students because we will be the driving force to make those changes happen. With that being said, here's the agenda of today's event. The event will consist of 2 halves. Within each half, there will be 2 keynote speeches, which will happen here in this conference room. They will then be followed by 4 symposiums of specific topics simultaneously. And the details about the room links will be posted here. Now, please allow me to introduce our first guest speaker of the day, Mr. Wang Yongli, the Minister Counselor of Education Section, Embassy of the People's Republic of China in the UK, to deliver his welcome speech. Mr. Wang, please take away. Mr. Wang, can you unmute yourself?
Okay.
Yeah, there we go.
Yeah, Professor David Caldwell, Pro-Vice Chancellor, University of Cambridge. Professor Xu Tian, Vice President of Westlake University. Professor Liu Huiyun, University College London. Dr. Xia Junfei, President of CSSA Cambridge. Fellow scholars, students, good morning. 大家上午好. It is a real delight to attend this forum today. As an organization that provides support and services to Chinese students and scholars community in the UK, particularly considering the context of the current epidemic situation, it really gives me a great pleasure. And in fact, I'm very much encouraged to be able to witness the opening of this online academic forum organized by Chinese Students and Scholars Association in the UK. So first and foremost, please allow me to give a sum up to the CSSA Cambridge and the CSSA UK for your excellent organizational work, and also please allow me to express our great gratitude to all the respected university leaders, scholars, and academics who are present today. To be honest, I'm not an academic, and I don't understand the academic topics that you are going to discuss about today. However, I do know that the development and the progress of human society cannot be achieved without scientific research and international academic exchange and cooperation. At a time when the world is facing a great threat from the new coronavirus, success can only be achieved through global cooperation, especially cooperation among the scientific community. As China is a country with a large population, we support young people to study abroad, to learn about the world, learn about the excellent cultures of different nations, and promote friendly relationship between China and other countries. To integrate into the world is our original aspiration and mission. Regardless of the epidemic prospect, the Chinese government will not change its determination to further expand education and continue to support our young people to study abroad. This will be no change in the policy of building the community with a shared future for mankind. 3 days ago, the Chinese government unveiled its policy report titled Guidelines on Accelerating and Expanding the Opening of Education to the Outside World, the New Era. These guidelines are issued against the backdrops of China's decisive battle to complete the building the moderately prosperous society in all aspects and the fight against poverty, education opening to the outside world aims to effectively prevent and diffuse risks through optimizing the overall layout, vigorously cultivating talents, breaking institutional barriers, and participating in global education collaborations, and enhancing the contribution of Chinese education to the world education development. The guidelines once again demonstrated to the world that China has been adhering to the concept of win-win cooperation and is committed to deepening and expanding mutually beneficial cooperation and exchanges in the field of education with countries around the world, and to making contribution to the building of a community of shared future for mankind. I wish the forum every success. Thank you. 谢谢.
Okay, thank you very much, Mr. Wong. And coming up next, we're honored to have Professor David Cotwell of Superconducting Engineering, Pro Vice Chancellor for Strategy and Planning, University of Cambridge. He is a fellow of the Royal Academy of Engineering. And let's welcome Professor Cotwell to deliver his welcome speech. Professor Cotwell, please take away.
Okay, well, good morning, good afternoon, good evening, everybody. As we heard from our organizer, I'd just like to thank the organizers for inviting me to present at this very important forum, which is my pleasure to do so. So I'll be speaking mainly on behalf of the University of Cambridge today in my capacity as Pro Vice Chancellor, but I will also share some personal reflections, which I hope you'll find important, and I'll indicate where they are. It's very nice to see that we have a very broad range of technical topics on today's agenda. We have a very wide range of universities and industries involved, in fact, from 3 continents. And timing is extremely important given the unprecedented challenges we face globally. Obviously, we have COVID-19 and we're all working out how to cope and exist, and in some cases even survive. But the implications for the future are very different in the way we conduct our work, our teaching, our research, and how we interact with one another. I think the notion that we would be having major successful conferences that run largely very well, completely remotely, that we've developed over a period of 3 months, would have been unthinkable a year ago. The fact that entire university curricula can be put online, and previously universities with no online provision are now completely online, all within 6 months. We have academics and researchers all around the world fundamentally changing how they operate. And what we need as a community is a ray of hope. We need something to look forward to. We need to believe that in the future, life won't just be as good as it was before, but in terms of our professionalism and our different areas of study and research, things can even be better. So we have a huge learning opportunity here, and we have to take it. We shouldn't underestimate the challenge, but we need to remain optimistic and confident. And that's what scientists do. Scientists don't look for problems, they look for solutions to problems. And that's what we're going to have to do globally as a result of the challenges we face. I'd also add that we have a recent global concern about issues to do with racism. And these have been unaddressed for decades, even centuries. And again, this gives us yet another opportunity to do actually what I think most people in academia always do. And that is to make appointments, to judge people on their technical output. Race doesn't come into it when you're choosing the best postdoc for your project. The candidate, the student, the graduate who is most qualified and most suitable for that work gets the job. And that has to continue. So what I wanted to do was to begin by giving you some context of my background and why I was particularly pleased to give this presentation today. So back in 1999, I was appointed admissions tutor at Fitzwilliam College, a position I held for 13 years. And like all new admissions tutors, I needed an initiative, and my initiative was to bring in more international students at undergraduate level to the University of Cambridge via Fitzwilliam College. So in 2001, I made my first visit to China. I've now visited China more than 100 times. I initiated a scheme to recruit undergraduates directly from mainland China. And this was the first scheme of its nature in the UK. At that time, Cambridge recruited from Singapore and Malaysia, but we extended that scheme to China. And now we send a team of 9 senior professorial interviewers, including me. So every year I travel to China and we spend a week interviewing students who are studying in mainland China. So rather than make them come to Cambridge, we go to them. And we get many hundreds of applications each year from mainland China, which generates some extraordinary students. So we've worked hard at this scheme, but we're absolutely committed to developing opportunities for Chinese students. At graduate level, the Department of Engineering, when I was head of engineering in 2014, had more Chinese graduate students than it had UK students. So the University of Cambridge, the technical subjects within Cambridge in particular, have a very well-established track record with taking Chinese students. And that really underpins a really important culture in Cambridge. So very bright students from overseas make everybody work harder and better. We raise standards, we are more eclectic, and the message that goes out to the world is that we're open for everybody. And I know there are many concerns within China at the moment that Britain and other leading Western universities are not welcoming to international students. That is not true. We're making as much effort as we can to reinforce the message that Chinese students are extremely welcome at UK universities, but from my point of view, Cambridge in particular, so they understand there is a future, there is a career, there is an educational route for them. As part of my role as head of engineering, I also initiated the first formal overseas collaborative research centre between the University of Cambridge and another organisation. And that's the Cambridge Nanjing Research Centre, which is currently under construction and is due to open next year. And that offers a number of exciting opportunities. So over the years, I've also taken many Chinese research students. So 80% of my research students have all been Chinese. So what I'm trying to say is that I think I've got a very good background and I'm well qualified to speak to this forum. And I'm absolutely committed personally to developing opportunities mainly for young people, but generally between China and the UK wherever I can. So I think we should talk a little bit more now about opportunities and how we might manage them. We have a real opportunity to coordinate activity and to support one another more than we've had before, as I've mentioned. But one thing I would like to say is that everything has to be funded. So I don't think funding should be the main driver. I think academic output and technical input should be the main driver. But we have to acknowledge there are actual costs for what we do. And one particular concern I've had for many years is that there are very significant differences between the UK and the Chinese education system, particularly at school level and at undergraduate level. And although there are many funding opportunities for Chinese graduate students in the UK, there are virtually no funding opportunities for undergraduates. And it's very important to realise that Chinese undergraduates form a very important feeder line for Chinese graduates. And until we can get the funding sorted out for Chinese undergraduates, we are going to have a big problem. And many times I make this appeal when I'm speaking to mayors, deputy mayors, ministers, funding organisations in China. And the outcome is usually more funding for graduates. So there is a real need to fund undergraduate education of overseas students within the UK. And I think that is something that needs to be generated from within China. Okay, so how are we going to take all this forward? Well, in my view, it's pretty clear. It's organized, coherent collaboration. And emerging technologies really rely fundamentally on collaboration. Individuals working on their own will always be limited in terms of their output, and we're better and we're stronger together. So I agree entirely with the comments of Minister Wang, actually. Collaboration is key to success, but my personal opinion is that we need to think differently. This is not just about engaging in research where we have specific bits of funding, which we then give out to individuals, we do the work and we walk away. I think we need better, more defined drivers than that. I think in terms of universities, academic drivers have to come first. And if you look at what universities are good at, it's taking an area at a relatively low level of technological readiness and developing that area to a point that it can be developed by commerce and industry across the world. But the key thing is in that early period of development, universities and industry need to collaborate carefully. We don't have a job and industry has another job. We have a collective job and we need to work together at each stage of the process. We need senior leadership to actually get behind this and to back this and to be creative and to encourage and provide an environment for effective collaboration. But again, in my view, old people like me won't determine the outcome of this. This is a young person's game. And senior leadership may facilitate, but it will be the young people that deliver. The bright young brains, the individuals across the world, but particularly in the UK and China, who don't believe that they're going to fail, that they believe they will come up with solutions. And it's that energy, it's that drive, it's that commitment that will take us through. So this is a young person's problem. Senior leadership needs to facilitate, but it's the young people that will deliver ultimately. We can think a bit about how the models of collaboration have worked so far. And again, these are just my personal views, but I always find it really frustrating that industry has a fairly narrow view of what they want to fund and what they don't want to fund. And quite often industry will say, we will give you X amount of money, go and solve this problem. And I don't think that's the way to do it. I think industry should meet academia and say, we have a problem, we're interested in your views on the solution. And together, the solution is worked on. And universities are a huge resource. But quite often, industry insists on having constraining intellectual property rules, which actually choke work in a university. So it's very rare, if you're working on something of low technological readiness, that it's going to produce a huge amount of income in the short term. So my advice is, don't tie universities up with long contracts that prevent them communicating virtually anything they're doing. Do the opposite. Tell universities what you want to tell them that won't harm your business, but let them run with it. Let them communicate it widely. And that way you'll fund one project and you'll have many other academics involved with it. You'll get the benefit of an institution, not just one individual. And at the end of the day, when we start to develop things that are commercially sensitive, that's when you have fair agreements with universities that restrict the communication of key results. But quite often these collaborations are stifled at the beginning because you can't get them running because there are ridiculous IPR constraints placed on universities which choke output. So I think we need to look forward in a different way to the way we've been looking so far. Obviously, the rest of the world is extremely important to China as it moves forward, and China is extremely important to the rest of the world. We have this mutual interest. We need to fully take advantage of it, and we need to move forward in a way that benefits the world in general, but specifically the countries and the continents that are involved in that collaboration. This is not just about China providing students to universities for which we can charge increased fees. This is about something much more than that. This is about a culture change. This is about observing that the cultural way of life in China is different to that in other countries, and that where we have these collaborations, we need to observe both cultures. This is about thinking broader, more broadly. It's about being more tolerant, and it's about taking opportunities as they arise. But most of all, it's about transparency. It's about nucleating projects, nurturing them, and providing a resource to see them thrive. And that's really important. So I think the best way forward when it comes to academic collaborations or industrial collaborations is to have key contacts in either academia or in industry. And those key contacts then drive the project. So I have a program at the moment with Shanghai Jiaotong University on superconductivity. There's a professor of superconductivity in Shanghai Jiaotong. He leads his side, I lead my side. He engages his group, I engages my group, and we have transfer of information and students. I go over there and supervise his students. He comes over to the UK and supervises my students. We've got complete openness and transparency. And the result is a series of academic papers that have been cited many tens of times, all because we collaborate. We don't give them money, they don't give us money, but it's absolutely a mutual interest to develop these projects. And I think it's a similar kind of ethos that we have to develop if we're going to take these collaborations forward. Okay, so I think I'll come to an end there, just to say that I hope you have a really good day. Unfortunately, I've got another commitment, so I can't stay for the rest of the forum, but the program looks extremely interesting. Hopefully it will be productive. I'd like to thank the organisers as well for this initiative. I think we need more of these types of initiatives that we need to engage with, and we need to publicise better where the opportunities are moving forward, because we get one go at this, we get one opportunity, and if we don't take it, I suspect it will be a long time before it comes around again. So we need to get going, we need to work together, we need to collaborate, and we need to be understanding. So thanks again for the invitation to speak, and I wish you all the best for the rest of the day. Thank you.
Thank you, Professor Cartwell, for the very inspiring speech and your efforts to in promoting diversities and pursuing excellence globally at the University of Cambridge. Thank you. So coming up next, we have our third welcome speech of the day from our host, Ms. Xia Junfei, the 36th president of Cambridge Chinese Students and Scholars Association.
Thank you very much indeed, Minister Councillors Wang Yongli and Professor David Caldwell, for all your inspiration. The distinguished speakers, professors, researchers, scientists, ladies and gentlemen, and all the students from all around the world. Good morning, or afternoon, or evening, or night, no matter what time it is, or where you are from. Please allow me to extend my warmest welcome and gratitude to all our invited guests and audience. My name is Junfei Xia, who is the director of the forum and also the 36th president of Cambridge Chinese Students and Scholars Association. First, I would like to really appreciate all the fellows and professors and young scientists from the world-leading research institutions and high-tech companies. We know that it is really hard for you to make decisions during this special time to share your experience and research ideas, especially on this complicated international situation. We know that it became more difficult for our international students and scholars to exchange our thoughts and ideas. However, as one of the young researchers, I sincerely hope that this forum can really encourage our young scientists to exchange their academic experience and collaborate with each other to build a better world for all our human beings. Today, we're gonna look at the future of our technology and what is the emerging technologies for our next few decades. If we look back to the great discovery in history, our human really made huge efforts to understand this world. such as the discovery of the gravity, the atomic model, electronic and magnetic relations, biological inheritance, the uncertainty principle. And based on our experience, we created and innovated many useful applications such as computers, genetic modifications, automobiles, telephones, solar cells, and rockets. Our technologies developed exponentially and are with significant discoveries, but still we know little about this universe. The discoveries of the last decades also reached an amount of achievements in many aspects. We detected the first gravitational waves, shake up the human family tree, took pictures for black holes of the cosmos as never before, tried to make interstellar first, tracked down the God particles, the Higgs boson. And we also made great contributions to the world and people's life by using technologies. We try to build up a simple virtual online world for good trading, tax calling, food delivery ordering with the smartphone app ecosystem. We started to implement genomics and precision medicines by gene editing. We stored our data to the cloud by large bandwidth network connections. We let the machine understand us by natural language and vision. Applied artificial intelligence in many aspects. We tried to break through the physical limitations of electronic devices to follow up the Moore's law. Thought about photonics. We tried hard to find vaccines and solutions to defeat the pandemic. We started to think the world with quantum mechanism, so using its feature for communication and computing. I believe that our technology for next decade will be much more advanced than present. It's predictable that more intelligent automatic devices and robotics come to us. Faster, higher bandwidth communication network will emerge to change our life by using VR, AR to provide immersive experience. We may use gene editing techniques to treat some diseases. But please, when we look up to the future sky, don't forget to look down at your current feed. I appeal our young talents to be wisdom, open-minded, for embracing the changes, challenges, and disruptive ideas, to be rigorous for fully and deeply understanding your research project. Let us be collaborative towards a borderless world for science and innovation, and our humans will step further and never stop to make the world better. The year of 2020 is just the beginning of the next 10 years. Although we've met the challenges and disappointments during the past 6 months, chances are that the world and our lives changed rapidly. You can leave yourself within a cyber world to learn what you want, to solve the problems you met. I believe a number of great ideas and thoughts are on the way. So please be confident, optimistic, and enthusiastic to fit yourself to this new life rather than to make the world suit you. Finally, I would express my thanks to those associations and societies to support for us. We will hold more online academic seminars and talks for you in the near future during this special time. And thanks for all to attend this event. Hope we really have a good time to travel around the state of the art in the following areas of interest and to envision the emerging technologies for the next decade. Enjoy it and thank you.
Thank you very much, Mr. Xia Junfei. Now we'll have the first keynote speech of today, but before that, I would like to encourage our audience to type your questions in the chat, so we will pick most representative ones during the Q&A session. Now, please allow me to welcome Professor Xu Tian, the Chair Professor of Genetics and Vice President of Westlake University. Before joining Westlake University, Professor Xu Tian was the CNH Long Chair Professor of Genetics at Yale University, where he also served as the vice chair of the Department of Genetics and the special advisor to the president of Yale University. He is a fellow of the American Association for Advancement of Science. Professor Xu's work mainly focuses on the mechanism of growth control and new genetic and biotech methods. He served as the president of Chinese Biological Investigator Society and the chairman of the U.S.-China Frontiers of Science Committee. He served as editorial board member of multiple journals, including Cell, Annual Review of Genetics, Molecular Cancer Research, Integrative Biology, and International Journal of Biological Sciences, and is the founding editor and editorial board member of Disease Models and Mechanisms. And now I'll give the stage to Professor Xu. Please take away. Professor Xu, you are muted right now.
Okay, all
yeah,
right.
There we go.
Okay. Hi, everyone. It is absolutely delighted to participate in the event. And thank you for the organizers. And also thank you everyone participating in the event. And it is absolutely delighted to be able to talk to you and to meet with you online and from Hangzhou, the city, and where Westlake University is located. And let me see that. Do you guys able to see my slide? Hello? Do you able to see my slide?
Not yet. Are you sharing screen? Okay.
Yeah,
I'll give you the permission. Sorry.
Allow it. Yeah.
Yes, it should be fine now. Go ahead.
Okay. Great. Let me share this.
Yeah, it's on.
Okay. Great. You can see it, right? Okay. So fantastic. So I thought that you know, this is a very interesting topic and what are going to happen in the next 10 years. And it's very difficult to predict into the future. But I thought I will spend the time to tell you a little bit about what we have been doing and what we have done. And hopefully that will give you some insight of, you know, what I thought maybe what are going to be happening in the future. And so as our organizer introduced, that I have been teaching and doing research at Yale University for 25 years. And in 2018, I returned to China and work with Professor Yigong Shi to start Westlake University. So I'm now full-time at Westlake University. And in addition to doing basic research in my lab, and I have also been working on translation research. And today, what I'm doing is that I'm gonna mostly spend time tell you about our translational research, and then to also at the end, give you a glimpse of what we're doing in basic research and in the lab at Westlake University. And hopefully this will give you a flavor of both type of things that we're doing in China. And hopefully that will get you excited. So let me actually first go into and introduce a problem to you. So drug development. And drug development is a big deal. And the big deal is because it takes a long time, and on average 14 years and 28 billion now to develop a new drug. But the drug saves people's lives. However, it takes enormous time that actually incredible resource to really to able to successfully develop a drug. So this slide actually shows you the pipeline, how to develop a drug. And in the traditional, not traditional way, I would say in the way that the FDA of the United States has been pushing for the last 50 years. And what you see is that basically you need to have a target. And then after target, then you basically to really screen through a compound library to get a small molecules that hit the target. And then you validating that in tissue culture cells. And then after that, you validating animals. And once you're validating animals, now you can put in trials in humans, clinical trials. However, the successful rate is extremely low. And actually, indeed, when at the first half of the process, from a target to testing in animals, the success rate is 1 in 1,000. That's extremely low. And after it succeeded in animals, now you're testing in humans, actually the success rate is reasonable. It is actually more than 1 in 10. So the reason that actually the first part of the process is not that successful, it is because we think we know the mechanism and by molecular mechanism, but the in vivo mechanism is extremely complicated. In vivo, a lot more complicated than we think. And that's why many of them mechanism based on target based, molecular based, and then when you test in vivo in animals, they fail and 1 in 1,000. So what we have been doing in China and in the last several years is that we actually develop in vivo system. And indeed, if you look at it, and right now, the Western medicines, more than 50% of the Western medicines, Western drugs are not developed in this way. Actually, more than 50% of the Western medicines are developed initially by directly giving drugs to humans and to show that it works. And indeed, many of those are developed by herb medicines, and then identify the active ingredients and to become Western medicine. So we cannot directly testing these drugs in humans now for ethical reasons, but we can actually using animals. So what we are doing is really looking into what are the successful approaches that in other research and in other biological research. For example, in the successful researchers that successfully dissected developmental biology, dissect the signaling mechanism, dissecting cell cycle regulation, apoptosis, growth control, etc. So what we have been doing is that the field have been choosing a biological phenomena and then choose model organisms, animals that exhibit that phenomena. Then you basically systematically mutating genes to see which genes mutated. Now you can disrupt the process that you're interested in. This way, you identify the genes involving the biological process. Then by studying those identified genes, you can understand the underlying mechanism. So using that approach, and my lab in the past 2 decades, basically identified all the key regulators for growth controls. And these are actually multiple and signaling pathways regulating growth size control. And these things determine how big the animals are, determines how big our organs are, and why our organs are proportional. And furthermore, we discovered that these genes, when they mutated, they actually cause diseases in humans, and more frequently, they cause cancers, because cancer indeed deregulation of growth control. And so majority of the pathways and almost all the pathways and their components regulating growth control are initially identified in my lab. And we're very glad that actually more than dozens of drugs are developed based on the pathways we elucidated. So what we try to do is they say, aha, now you can dissect biological mechanism this way. Why can we develop drug this way? Why can we identify novel drug target this way? That is, by choosing a mammalian models and then choosing conserved disease processes, then use systematic mutating genes in animals to see which genes, when you mutated, it disrupted, you can stop the disease. This way, you identify novel drug targets that could develop drug to stop the disease. And indeed, sort of we are very successful and develop this. And now by mutating genes, there are multiple approaches have been previously developed. And for example, genome-wide actually knockout approach. And these are developed by America Packy and Martin Evans and Oliver Smithies. and they actually win Nobel Prize for knockout approach. They are mutating genes in mammalian cells and then in animal. More recently, CRISPR-Cas9 can mutating genes in mammalian cells. However, both approach, you needed to actually inject fertilized eggs, then surgically putting the fertilized eggs into foster mothers and then to produce animals. And these methods are very successfully mutating individual genes that you're interested in, but it's too expensive, too costly, and take too long to do genetic screen. You cannot do that in live animals and to do the genetic screen because it's going to cost, I showed here, and $17 billion to $20 billion, 20 years, and to just go through the one genome, and you cannot do that. So we developed a new method, and the method is really based on concept of transposon that initially discovered by Barbara McClintock and is shown in maize. And she won Nobel Prize for finding these mobile genetic elements. And in the 70s, they Boston using transposons dissected bacterial genetics. In the 80s, Joe Rubin and Spradling and using P-element transposons revolutionized Drosophila genetics. Eric Meyerowitz using tDNA doing insertion mutagenesis in plant in the 90s. However, systematic dissecting and genetic and transposons in mammals, in human cell, was never successfully developed. So we actually successfully developed the technology in Fudan University that allow us to systematically mutating genes in mice. Not only that, these are actually can be powerful tools during gene therapy, and which I will mention a little bit later. So basically, after done that, these transposons can mobilize and in animal germline by themselves without any other injection manipulation. So this way we can just breed animals and mutating genes and look for genes that actually can stop diseases. And indeed, so what we did is actually we using and to look for actually diseases cause inflammations. And this is a show that actually we identify novel target that can stop actually inflammations and caused by this colitis, this inflammation of the gut. And we actually successfully identify novel target and develop drugs and to really show that actually you can suppress and the development of inflammations. And indeed, these we also develop drugs to actually for immune oncology, and this shows that actually treating different cancers in mouse models, and we are launching clinical trials this year. So also want to now move a little bit to some other things that we developed. When we actually map a growth control pathway and suggest that one of the drugs, rapamycin, potentially could be treating for cancers. And physicians in the United States actually using rapamycin to treat bladder cancers. And what happened is that, interestingly, 1 out of 35 patients worked. And people are puzzled why this one patient worked, why others did not work. At that time, and we developed sequencing machine. So physicians actually sequenced the individuals that actually worked and discovered that indeed the individuals have genes that are in the pathway we deciphered that are mutated. And so indeed, NIH launched 2014 Miracle Responder Program to looking for individuals that respond for drugs and to see whether the genetic alterations corresponding to these drug responses. And that indeed to show it working. And in 2015, Obama launched Precision Medicine Program. And we're very glad that our research contributed to the launch of the program. So precision medicine, the individuals, the patients that mostly could benefit from that is indeed actually a genetically inherited disease patients. There are more than 7,000 hereditary diseases. Each individuals have this disease because individual genes are mutated. Now with the ability able to sequence the human genome, we can identify which gene mutated. and we can put the normal Y-type gene back for gene therapy. And indeed, that's why we developed a new company, and Giselle. And with our technology, the transposon, we can actually put normal genes back into patients and indeed can actually treat this disease. And the piggyback transposon we developed has now been used for multiple diseases in gene therapy. And we also started clinical trials this year, and in a different company called Giselle Therapeutics. So also want to tell you about another area for translation. And we actually are one of the first company in the world and to using AI for drug development. And we actually initially started AI for biomedical research in 2013. And then we developed novel AIs to actually match drugs to different clinical indications. And the success rates are very high. And in 5 years, we have 4 drugs in phase 1, phase 2, phase 3 trials. And so I'm not going to go into the detail of how we did it. And it really, I think it's to show the power of combining traditional drug development program with AI, and this to show the drug. And I want to particularly mention this drug because we have worked with the Zhejiang University #1 hospital to show that this drug works for coronavirus, suppress coronavirus. And clinical trials will be launched this month at Yale, simultaneously at Harvard, and for treating coronavirus and using our drug. And I'm very proud. Hopefully they will all have good outcomes. So I want to also tell you about another areas that we developed. And this is in the area of natural products. And natural products are actually everywhere in our life. In the drinks we have, in the fragrance we use, and as well in medicines. And the bottom two, I show one if artesunate. And artesunate is Qinghao and Qinghao Su. And Tu Yu originally discovered that actually her group discovered that Qinghao could actually suppress malaria. But it took 30 years to identify the molecule, Qinghao Su, artesunate, and then synthesize and halfway synthesize the molecule to make it develop into a drug to give to patient. And 30 years is too long, take too long to do that. So, and my friend, Professor Jinke Wang and of MIT and I, we start a new company. And basically using AI, genetics, and synthetic biology to identify the active ingredient in herbs that actually have the biological activity. And this is a very complicated process because each herb has thousands of different compounds. And how do you know which compound is active? This is a complicated biological process. And indeed, this is perfect for AI to solve. And we combine with AI, system biology, genetics, and to identify the compound, as well as the enzymes that synthesize the compound in plants. Then we can actually clone the genes into yeast and to fermentating produce the compound. And we're very exciting. And multiple actually drugs have been now under development. And we already have several of these compounds that are already produced and nutraceuticals and are ready to release this year. And we also very excited that actually work with Jonathan Rothberg. Actually, we actually have an incubator, the Rothberg Institute next to Yale. And in the last 20 years, the incubator have successfully developed more than 10 companies. And 3 of those are sequencing company. And the 454 Life Technology is the first sequencing machine of the world. And actually the first human individual sequence, Jim Watson sequence, and the first cancer genome, the first microorganism genome, and many firsts are done in our machine. And we also developed the first sequencing on chip, iron torrent. And right now, we're actually developed the first home use sequencing machine. When you get up in the morning, you don't feel comfortable And after you brush your teeth, you can actually sequence to see whether actually you have an infection. If you do have an infection, you should go to hospital. Otherwise, you should take a day break. And the key to solve that on two fronts. One is that to home use, you need to avoiding vibration, because the vibration not allow you to develop sequencing easily. And the second, home using, you cannot send your data for informatic individual to analyze it. That's too much, too costly. So we combine with AI, with new technology, and we actually have the first home using sequencing machine. And in addition, we are developing the first protein sequencing machine in the world, because the majority of the human diseases are diagnosed because of protein, not DNA, not gene expression. And we have now are developing the first protein sequencing machine in the world. This just showed what happens of the sequencing machine. And the sequencing machine basically dramatically changes cost structure. And the cost structures, for example, when you buy a expensive sports car, it costs you 100K. Now the costs have been reduced so much, you can get it with 1 penny. That's how much the cost structure changed for sequencing. And that's why you see dramatic applications of the sequencing technology. And we're very proud. We sequenced Jim Watson's genome, the discovery of DNA. We also sequenced Gordon Moore's genome because he's actually the founder of Intel. We also sequenced Townsend's genome. He's the inventor of laser. We, using laser, code Townsend's genome sequence and beaming out of the outer space. Hopefully one day, intelligent beings in the universe will receive the signals and from Earth and about a human genome. We also developed a new mobile NMR machine, because NMR machine is too expensive and too costly. And also you need to unplug everything before you can examine. And that's really too costly. So we have developed Hyperfine, and we developed the first world mobile NMR machine. And in February of this year, and FDA just approved the mobile machine, and it can be moved next to patient's bed, and it can be also put on ambulance and to check on patient at the accident sites. We have also developed another thing. And when you go into hospitals right now, people are using stethoscopes and to listen to your heart to see whether your heart's beat normally, to listen to whether you have an infection. This technology is 200 years old. We think that's actually too old. So we have developed the world's first handheld AI ultrasound device. And in the past, all the ultrasounds are using pressure crystals. We have developed a CMOS chip and allow us to minimize the device and handhold and then directly see on your cell phone. And this actually changed everything. And this is a whole body and ultrasound device, and approved for all different parts of the body. You just need one. You don't need a different crystal, different detect heads for different parts of the body, like the old ultrasound machine. And this really shows that you can actually, more than 10,000 physicians have been ordered this machine. And we're very proud, because in a year or two, when you go to hospital, and it doesn't matter where you're in the United States, in Britain, in other part of the world, and you will see physicians on the neck is our device, not the stethoscope anymore. We are very proud because we changed the world. So all these things actually develop under one kind of thinking. In 2014, when we discovered the future development of the incubator, and we have developed the thought that in the past, what really changed the world is the cell phone, is a smartphone. Really, basically, I control my own information. All my connections, friends, contacts in the cell phone. And you want to search information, use your cell phone. You want to buy something, use a cell phone. And what I believe is that in the future, in the next decade or so, what we need to focus on is that I control my own health. That's what's going to drive everything. Imagine you can actually have this thing that control at your home. The handheld ultrasound device is only $2,000. It's like a blood pressure machine you can put at home. And we actually have saved people's life, because when you have a heart problem, you go to the hospital and check it. Maybe it's already over, the episode, and difficult to know. And when you have an episode, you should check at home. If you have a problem, you beam the information to the hospital. And indeed, this is what actually we have been in the last year's board meeting, and a physician and his father thanks us. And this is a video we played because it actually saved the life. And this could completely change how medicine is practiced. And just like similar to home sequencing machine, and all these things going to change people's life, because it can happen at your home and you can know what happened. And before the disease develops into a serious condition, you can already know. And this saves life and reduce the cost. So what we're doing is really look at it on this graph. It really dictates that in the last 200 years, and the human society are moved by waves of technologies. And from 1771, and Richard Arkwright in England, that are using hydropowers and for fabrication, and to actually 1825, George Stephenson's steam machine for railroad transportation, and to Carl Benz's engines, and 1886 to right now the current waves, and 1939, and computer science. Right now, if you look at it, and biotechnology has just passed the 30-year incubation period and into 10 years production period. And the next wave, of course, is artificial intelligence that actually based on neural network, and has just passed the 30-year incubation period. And what we're doing is combine these two ways of technology to drive forward. So I'm gonna very briefly touch on the basic research we're doing in the lab, in the Westlake University lab. This is initiated and in a discussion between Kevin Kelly and myself in 2018. And we discussed whether AI robots will terminate mankind. And KK's idea is that it will not be, as long as we can educate AI similar to the way we educate our kids. And he thinks that this is not gonna be, because he reasoned that actually we educate our kids does not kill parents, does not just go out to terminate human beings. And however, I thought this is not that simple, because what happened is that humans, like other mammals, we have consciousness. We aware our existence. Only when you aware our own existence, you know the values of our own life, you can appreciate other people's life. If you do not even have the concept of consciousness, you will never able to appreciate others' life. That's why I thought it is absolutely important to understand consciousness or self-awareness. And this way, and in the future, when we have robots, and maybe the robots can also have consciousness and understand what are the importance of consciousness, therefore they will appreciate others' life and will not go out to terminate others' life. So we actually launched a research program at Westlake University to really dissect consciousness. Now, this is extremely difficult, of course, because this is the most miserable phenomenon in our life or in the universe, or most unknown. And although we every day we experience consciousness, without consciousness we're not functioning. However, if you describe what is consciousness, nobody can describe what is consciousness. We know nothing basically. So what we're doing is that we are actually really using animals and a patient and actually robotics and try to dissect and self-awareness. We are trying to work on really several fronts, and we try to understand the biological basis of self-awareness, of course, and mammals have self-awareness and humans. But we are also interested in the material basis of consciousness. We think these consciousness are fundamental features, fundamental sort of phenomena of systems of the universe. And these systems are most stable system in the universe, because when you have consciousness, you are taking energy, you are taking a molecule to maintain the system. And therefore, those systems are the most stable ones in the universe. And therefore, ultimately, they will be evolved in the universe. And there's a reason to believe that not only a biological system like ourselves have consciousness, and maybe the Milky Way also have consciousness as well. It's just because we have no way to observe and to dissect. And therefore, we are, in addition to dissect biological system, we are also using other systems, computer systems, AI systems, to develop to dissection for consciousness. Okay, at the end, and I would like to say a few words about Westlake University. Westlake University is a new kind of university. It is the first private and non-for-profit university in China, and for mainland China. And it is very exciting because it is the board of the Westlake Education Foundation accept donations around the world, and mostly from Chinese entrepreneurs and also from ordinary citizens, and then to form the board of trustees. Then the board of trustees selects president and the vice president to run the university. But the university is a special kind of university. It is also supported by local and also national government. For example, the campus is built by the local government to really, because this is an incredible opportunity that in the history, because not only individuals of the society wants to have this type of university, but also ordinary citizens wants it, and the government officials also wants it. It's a unique time of history that all sectors of the society actually want to world-class university in China. And we are very, very proud to have peoples in all sectors of society, and from private companies to ordinary citizens to government officials, all support Westlake University. Now, the university that whether going to be successful is mostly relying on whether they have first class and professors. And I can tell you that we have now signed on 125 professors and 13 endowed chair professors. And endowed chair professors have the standards that they actually have themselves either created a new field in the past, or they are actually the current leaders of the field. And with this standard, majority of the tenured professors at Yale University are not qualified, because you want to create a field that's not easy. And you are the one leading the field, not easy. And we're very proud. We have 13 endowed chair professors already. And our 3 deans, I can tell you a little bit about 3 deans. The deans of a School of Science, Li Deng, who is endowed chair professors from Brandeis University and the chairman of the chemistry department before joining Westlake University. He actually invented asymmetrical organic synthesis, and he's the Arthur Cooper awardees of this year. And the dean of School of Engineering, Yang Yang, is an endowed chair professor from UCLA, and who invented the transparent solar battery. And he's actually one of the 19 professors selected by Thomson Reuters in 2016 as the most influential professors in the world, one of the 19. And also, end of last year, we have Professor Hongtao Yu, and it become the Dean of School of Life Sciences. And Hongtao is endowed chair professor at UT Southwest in the United States. And he's also an investigator of the Howard Hughes Medical Institute. And Howard Hughes Medical Institute, there are around less than 300 Howard Hughes Medical Institute investigators. They contribute roughly 1/4 of the most important discoveries in the biomedical field in the world. And we're very proud to have Hongtao and join us. But we're even more proud are our junior faculties, because senior faculties, they are succeeded, they made it, they can go anywhere in the world. But our junior faculties, we have now more than 90 junior faculty join us. And every year, the quality of junior faculty had been dramatically increased. In 2017, when we made offers to the junior faculties, some of the offerees actually not join us. They actually joined Tsinghua and Beida. What that means is that at the 2017, the faculty we recruited at Westlake University are similar level at Tsinghua and Beida. I can tell you that we made 57 offers in 2018. None of those actually joined any of the universities in Asia, including Tokyo universities or Hong Kong University. We're very proud. But I did not tell you, say, hey, they did not join any of the other universities in the West. Some of them still joined, the best university in the West in 2018. In 2019, our recruits actually went another level because we have junior faculties give up University of Pennsylvania's offer, give up Duke's University's offer, give up NYU's offer, give up Cornell's offer, give up MIT's offer to join Westlake University. We're very proud because for junior faculty, their next career stage, the next 5 to 6 years, they're going to determine their career path. This is the most critical period. When they give up MIT's offer to join Westlake University, this means they believe that Westlake University is the best place for their career development in the next 5 to 6 years. And that's why we're extremely appreciate that these individuals that give up those offers to join Westlake University. Now, many of you may ask a question, what Westlake University could offer that other places are not offering? I can tell you a little bit. And in 2018, when I returned to Yale, and Yale's president, Peter Salovey, and joked with me, say, hey, Ken, how can you desert us? Because I received my PhD at Yale, and then I was on the faculty for 25 years. And he even joked, say, hey, I heard that you guys try to pass Yale. Now, this is a very difficult question, okay? Because indeed, if Professor Yigong Shi and myself and others, if we do not want to build a world-class university, we're not gonna come to Hangzhou. Absolutely, we want a world-class university. But how do you able to do a university in a relatively short period of time can surpass, areas that are Yale, for example. Yale has 300 years, and Cambridge and Oxford have 500 years, right? And if we can do the same, it's gonna take too long to do it. I can tell you some of the things of what we're doing. For example, what do you see? This picture is our new campus. And the 3 schools, School of Engineering, School of Science, and the School of Life Sciences, they're all connected by academic ring, physically connected. So professors, students of biological science can actually meet professor of chemistry during lunch. And a student, actually postdoc of mathematics, actually could walk into seminars that actually computer science is running. This way, physically can bring different principles together, cross-disciplinary interaction. And we actually have offer grants that if 2 professors actually they propose a cross-disciplinary research, we give money. We actually have a student could have 2 different professors that actually from different field to co-advisor. Things like that, very difficult for old university to do, because older university and they building one building at one place, one department at one location. They're difficult to have people at different principles and come together. That's what we can do. And that's what we're doing. And I hopefully that we hope that when we doing this, and then new ideas and new theories will come from this cross-disciplinary interaction that actually will be a fertile ground that at other places that cannot happening. And we also, every other weeks, all professors come together to discuss new discoveries and the new ideas of different fields. And that's not happening at Yale. and not happening actually anywhere in any other place in the world. And indeed, we have a Cambridge professor came visiting us, give a seminar afterwards, and he actually insists want to join our news and idea program to discuss different ideas when you have professors in different fields presenting these ideas. And I also want to tell you that this is actually happening in Westlake University because we not only have system that actually works for world-class university, board of trustee that appointed president and vice president runs the university, but we also have the support of government. And for this new campus, without government support, will not happening. And that's indeed, we are combining the best of the world and to develop a university of a unique kind, and hopefully that it will be in select areas and going front of the world in a small number of years. And I will end here and thank you for your attention.
Oh, thank you, Professor Xu, for sharing your very extensive academic and industry experience, and also telling us all about the Westlake University. And I hope the clinical trial of your new drug against the COVID-19 will be a success, so we can fight off this pandemic sooner. Now, yeah. So now, while we're waiting for the questions to kick in, I actually have a question about drug development myself. So I'll just go ahead and ask anyway. So Professor Xu, I would like to know what is your opinion on closing the gap between animal models and clinical trials? I know animal model is probably the best or the closest we get away from clinical trials, but many times they don't really predict what's going to happen in human body. Do we have any better alternatives? Maybe will allow us to bypass the ethic issue with animal models as well. Thank you.
Yeah, so great question. First, you need to choose conserved biological processes when you use animal models to predict whether drugs will work or not, because humans are indeed very different from animals. So if you choose a biological system that are different, then they have very low predictability outcomes. But also their new technology continue evolving. For example, and these new technology organelles, and I don't know whether you know that. And these organelles are actually not tissue culture, not individual cells that are grow in a medium, but they actually organize in a tissue, similar in a tissue fashions like in the human. And they, although these are in vitro systems, they are able to offer some of the features that are similar in tissues in human. And we believe these will have good, predictable powers and for drug development. And there are other individual technologies that have been on the merging. And I think that we are getting better and better. But still, you're absolutely right. This drug development business are still very, very inefficient, incredibly inefficient, I would say. Takes 14 years just to develop one drug. Takes too long for everybody, too long for investors, too long for scientists, mostly too long for patients. And so we urgently need people in different fields and to join together to improve those drug development programs. And I was impressed when AI people joined us to develop drug, and this actually we develop much faster and when predict. So I think people from different disciplines come together can really make a big difference.
Okay, thank you very much for your answer. It seems like AI is going to be the next game changer. Okay, let's see if there's any other questions we have. Okay, can you also comment on the consciousness point you just mentioned? Do you think there's a molecular imprint associated with, consciousness? To be more specific, for example, if, like, say 2 days later, we're both thinking about this conference, are our brain pattern going to be the same, or are we going to generate the same kind of molecule to kind of think about this event? Thank you.
Great question. And I must say, I have no clue. Okay, so this is the most mystery sort of phenomenon in our universe, and it is probably the ultimate phenomenon. And to have a consciousness and to have self-awareness is an incredible thing, and we literally will know nothing. And that's why. And you'll be surprised why Westlake University would want individuals like myself to study that. And that's indeed Westlake University is. And we are trying to really have work on very difficult questions and have our professors, and hopefully that once a breakthrough that will have a significant impact. And as Professor Yikong Shi said, what will be successful for Westlake University in the future? Of course, the students and the postdoc that we train, and if they go out and have a very successful career, that's our success. But also, how do we measure other aspects? And we think 2 areas. If in the next 10 years, if there's 10 most important fundamental discoveries, for example, relativity, and we think if one of them come out of Westlake Lake University, that will mean that we're succeeded, okay? And also, we also try to work on key technologies. And similarly, if one of the 10 most influential technologies developed in the next 10 years, and if one of them that come from Westlake University, that means we're successful. And we're very, we do not know whether we're going to be successful, but we're working very hard. We have started gathering the best people in the world here. And you can see, for example, there's only 40 life science professors in Westlake University when this coronavirus outbreaks. And if you look at how many life science technologies in the rest of China, and there's a huge number, right? But if you look at the most important discovery so far, come from Westlake University, and the structure of the receptor from lab of Zhou Qiang, and more recently, and the biomarkers that potentially could predict the severeness of the development of the infection are actually from Guo Tiannan's lab and publishing Cell. And actually, indeed, and in the United States, NIH's report and recently really say, hey, not only in the past say the structure of the receptor for important for developed drug, but also for this biomarker and being raised in the highest level to able to to use the indication for how to actually predict the patient so we can treat the patient differently. And this is, we're very proud because you see, this is everybody on the same level, right? When this virus hit, but the individual could make a difference, means that they are the people that can bite the bullet at a difficult time when you have high quality people. And that's why, and Westlake University is just launched, is the Emerging Infectious Disease Center. And this is actually with the support of the government as well as the society. This is gonna be the second safety haven and for after the government CDC, because we hope that if next infection disease come out, and in addition to the government's CDC, there's going to be Westlake University. We'll be there, we're ready, and we can actually make sure that actually the society that will be best take care of. And the key is really to recruit the best top people. And these top people, not by numbers. The huge numbers of people are not going to make a difference, but the quality of those individuals going to make a difference when you have the best people. And at a critical time, these people is going to make a difference.
Okay, thank you, Professor Shi. I'm very looking forward to the potential impact that Westlake is going to make in the near future. So another question from Spark Sun. He asked, can the efficacy of Chinese medicine be quantified, such as double-blind testing? Thank you.
Oh, fantastic question. And indeed. So the Chinese herb medicine is really accumulation of thousands of years of experience. And it has a lot of, it's a golden mine. However, in the recent years, and because the field actually refused to combine and accept the modern science, and it has been left behind. And in the turn of the century, in the 1920s, and when Western medicine first actually come to China, and because the Chinese medicine is very powerful at the time, so they refused to accept the new scientific concepts. And at old time, actually, the Western traditional medicine and from Greek and from Greece or other places, they're much less sophisticated than Chinese medicine. They're much more rudimentary. But the Chinese medicine is a lot more sophisticated. However, what happened is that the Western medicine, traditional medicine, they combine the element of science and then they move forward. And when dissection happens, when people saw brain, when people saw the heart, and they know the heart is not for thoughts. But the Chinese traditional medicine, Chinese philosophy believe the heart is for thoughts. And at the time in the 1930s, there's a huge debate and whether Chinese medicine should combine with science. But the conclusion is that it refused. They still insist that the heart is hold the thoughts, not the brain. And so many of the things actually since then, and when anything, any area, when you refuse to refuse to combine the new knowledge and the new and the world, and they're going to be behind. And so Chinese traditional medicine still has a lot of the incredible things. It's a gold mine. And however, need to actually combine with modern science. And that's what I move forward. And indeed, my lab is working on that. And we are actually using a Chinese traditional medicine and with, with genomics and with AI and to giving traditional medicine a scientific measurements and that allow to able to measure quantitative measurements for efficacy. And this way, I believe that actually Chinese medicine could do a lot and for the mankind. And but I think the solution has to be combined with modern science and technologies. Any other questions?
Thank you. Yeah, we can have one more. So there's one question asked about gene therapy. The question is how the so-called normal gene can be created and what the artificial made gene lead to some unexpected problems when it is integrated into humans.
Great question. So gene therapy and has been doing a lot of good. And gene therapy is the simplest way to develop drug. Because imagine, right, if you have 7,000 kinds of diseases are caused by a gene's defect. So if now you can just put a normal gene back, you should be able to cure the disease. This conceptually very simple, right? And you don't need to develop a drug. Drugs are very difficult to do. However, this simple said and done, it is because safety concern. When you put the gene back, how do you put the gene back? And so initially people putting gene back by a virus, carry the gene going back, but a virus have unexpected side effect. And 20 years ago, and UPenn gene therapy and an individual killed. That's what sets the gene therapy back for many, many years. But now gene therapy are coming back. And most recently, coming back because they put a gene back in the eye. Because in the eye, there's no immune system. So no attack on the virus vector. So the hereditary eye diseases have been now treated using gene therapy. But we have now developed other technologies and not using virus to deliver genes. And so this way you can also, have the safety issues and to be at a different level. And, but also very true. And the normal human genes are huge. Normal human genes are about 250 kilobases. And the traditional virus therapy way and cannot carry those genes. So right now, most of gene therapy are using abbreviated version of the human gene. And those genes, abbreviated agent versions, in some of the diseases are okay, but other diseases may still have safety issue. And we have now recently developed technologies allow us to put the normal human gene back. That is a huge piece, and put back. But these are still need a clinical trial to demonstrate safety and for individual diseases, and it's still under the way. But it has shown great potentials, and human gene therapies and cell therapies, and in the therapeutic field, and the small molecules are most mature, and later on, and large molecules, antibodies, and proteins have now been treating more and more diseases, about 50-50 now compared to small molecule. But the new waves are coming, and the gene therapy and the cell therapy, and of course, and efficacy and ethical issue and safety are the three big pillars that actually really need to be on solid foundation before these therapies can move forward. Thank you for your attention.
Okay, thank you very much. So that should conclude Professor Xu's talk, and thank you very much for coming. We hope to see you again in the near future.
Yeah, and I just want to put one ad out that for potential students that are interested in our PhD program, you're welcome to apply. We actually have a huge number of students that actually did their undergraduate studies abroad and now coming back to Westlake universities and for PhD. And last year we recruited 18, and this year we probably will be recruiting 40 and students that are actually trained undergraduate student abroad. And also for young scientists, you're welcome to apply postdocs and research scientists as well as faculty positions at Westlake University. Thank you.
Thank you, Professor Xu. We're now moving on to our next keynote speaker. We'll have Professor Liu Huiyun join us, the chair of Semiconductor Photonics at University College London. Professor Liu received his PhD from the Institute of Semiconductor, Chinese Academy of Sciences. After receiving his PhD, he joined the EPSRC National Center for 3-5 Technologies at University of Sheffield. He was responsible for development of molecular beam epitaxy growth of semiconductor materials for the UK academic and industrial research community. In 2007, he was awarded Royal Society University Research Fellow and started his academic career in the Department of Electronic and Electrical Engineering at UCL as a senior lecturer. In 2012, he was promoted as chair of semiconductor photonics. Professor Liu's general interest concentrates on the nanometer scale engineering of low-dimensional semiconductor structures, such as quantum dot, quantum wires, and quantum wells. By using molecular beam epitaxy and development of novel optoelectronic devices, including laser detectors and modulators, by developing novel device process techniques, he has co-authored over 120 peer-reviewed journal papers in the area of semiconductor materials and devices. Now let's welcome Professor Liu. Professor Liu, you're muted. Professor Liu, can you hear me? You're on mute.
Okay, thank you. Can you see my screen?
Yes,
Okay.
please go ahead.
Thank you very much, Chairman. Good morning, Minister. Good morning, good afternoon, good evening, ladies and gentlemen. Thank you very much to let me in this forum and to show some overall thought and some overall recent results. My name is Huiyun Liu. That's my Chinese name. And I want to talk something about build up the bridge between photonics and electronics. So that's my outline. I'll first give a brief introduction in my group and what is molecular beam epitaxy. After that, I will talk why we need photonics in silicon microelectronics. After that, I will review the history in last 50 years, the whole world did with group 4 lasers, and also recent oral results in the area, finally give some predictions. The first thing, guys, what is molecular beam epitaxy or MBE? Actually, epitaxy is a Greek word that means build up on. So this facility is in the world for 40, 50 years now. Mainly is build up crystal on crystal. So for the crystal build up, actually, we can control the growth like materials in atomic layer, a fraction atomic layer. We can grow very accurately the materials. This machine we first invent like 1980s, 1970s. We never have the terminology about nanotechnology. And this machine can make something much smaller than nanotechnology in astron level. So that's a model of this kind of machine. So you can see, guys, it's more like a spaceship. So it's use ultra high vacuum in the machine and all the size and mass pressure. With ultra high vacuum, we can build up anything very pure materials, very high quality device. Actually, high quality device is critical for any semiconductor device applications like lasers, telecom lasers, modulators, detectors. So brief history of my lab. I joined UCL at 2007 October. At that time, I got the Royal Society Research Fellow. And I'm very grateful for UCL offered 2.5 million pounds and set a lab. At that time, just after my postdoc, I was really excited. But unfortunately, the reality is very hard. When getting UCL, I do find build up a semiconductor large facility is very difficult in central London. You can see until 2008 September, almost 12 months for me to find a lab where I can put my lab there. And the lab is a workshop or storage shop for some other department. Take a lot of political game or initiations and get space. Once we get space, and build up lab is pretty quick. We get a clean room done in 6 months. I have to say, guys, you can see this is a very basic clean room, and it costs 1.4 million pounds to build up a simple clean room to be used. Once we get the clean room done, so we get our facility delivered from US, Vico, the company. We have to block the street because London street is pretty narrow. And also London buildings is not allowed to knock the wall off, take the window off. We have to put the facility through a corridor, a small corridor in a very old building. So this kind of facility is very high vacuum. You can see here, the vacuum is about 10 to minus 11 torr, is very high. Because it's ultra high vacuum machine, actually it does need a lot of running costs. Even piece of metal with the capability for ultra high vacuum will cost over a couple of £1,000. So at 2010 January, Her Royal Highness Princess Anne opened our lab. Actually, she is a very kind lady. She asked a lot of interesting questions. The only question I still remember is she asked me where I was lived. I told her I live outside London. She cannot understand it because she has no idea how much is the professor salary in UCL and how much is a flat price in central London. So after that, actually, we slowly build up my lab. So that's the first mission, 35 MB, costs us 2.5 million pounds. After 5 years, we get another machine, it's group 4, mainly for silicon, germanium, tin, cost UCL another 2 million. And in the meantime, we also extend our lab, you can see here. And 5 years later, we get to the third MB. So that's another MB. We mainly focus on commercial applications or high stand device. So the third MB only cost MB is about 1.2 million pounds. So that's roughly the step we followed with my lab. Now we talked about why we need a laser on silicon. So first thing, guys, is a very short-term challenge. The challenge is for data centers. So you can see the data center, guys, the global data increased dramatically. So the problem, guys, silicon technology is very good for calculation, for dealing with the data, but it's not very good for transport the information between each chips. So nowadays we call corport light in. So basically we want the communication from lasers, waveguides, or fibers, but use chips to the calculation. That's a very short term. So recently, guys, you know 5G is very hot. Actually, 5G is one of this area. Another area is automobile or auto driver cars. So they need a lot of data and need a lot of sensors. That normally is photonic detectors, lasers, and dealing with the data. So this area at the moment is extremely hot. Another one is a long-term challenge. Actually, this challenge is for silicon microelectronics. So in 1965, Gordon Moore, he predicted the number of chips, the number of transistors in the chips is the number is doubled in every 12 or 24 or months, later become 18 months. The problem, guys, with this reduction, the size of silicon chips, the CMOS is getting much smaller. I think most guys work with photonics or electronics should know at 2018 August, Global Foundry announced this stop develop 7 nanometer below silicon CMOS. The reason, guys, is a big challenge to how to produce so smaller electronics. And another thing is the usage actually is not a huge market. At the moment, only company focused on that is TSMC. I think Samsung also try to focus the area, but the market is not that big because the cost is huge. And most company work on how to manage the chips, different structures, get faster. But one thing, guys, we can understand, doesn't matter the 7 nanometer or TSMC claim, they will have a 5 or 3 nanometer in the next few years. But the bigger challenge is close the physical limitation of a 2-atom space. That's some physical limitation we cannot overcome. So if it's near the end of silicon microelectronics, what's the future? Basically, guys, the commercial solution is you have multi-core chips. What do you mean multi-core chips? So basically, you cannot reduce the size to get the number of CMOS high. What we do, we put few chips together. So like your mobile phones, your computer nowadays, they have like a 8-core, 4-core, or 16-core. But the problem, guys, between the cores, use a copper connector. Copper connector is very thin and produce a lot of heat, and in the meantime, is a limitation for the data transportation. We all know this, guys, for your home, we use fiber optics. So basically, we need photonics to communicate each other, but use a computer to do the calculation. So that's a new area come out called silicon photonics. I don't think we can say it's new. The reason is for this side, this figure is from Intel. Intel worked in the area for a long time ago. That got 30, 40 years ago. Their idea is photonics layer, memory layer, and process layer. This picture is from European network website. So this also put the photonics with other stuff together. But I have to say it's a big challenge. So far, we still don't have a mature solution. The reason is, guys, the silicon. Silicon is very good for waveguide and also for the modulators, get very high speed, and also for very high speed for detectors. Also, we can get a multi-channel, different channel communication, and also we have a coupler between different devices. But what is missing? So the missing part is electrically pumped laser. So basically, guys, it's more like you have a pipe, but you need a pump. If you don't have a pump, so it will be no water in your pipe. So that's a critical part. So what's the challenge for silicon photonics? Why we cannot make lasers, the pump in silicon network? Guys, that's a nature. Actually, we get the God will. The reason is simple physics. So for compound semiconductor, like in phosphide, you have direct bandgap. So you have photons, electrons, communicating each other. So you produce light. But for silicon or group 4 materials, you have indirect materials to form this interaction. So we need have a balance of momentum. So for any reaction, doesn't matter. The physical law is doesn't matter what kind of materials, you need a balance of momentum and a balance of energy. So for this one, you don't need to consider momentum because it's easily balanced. It don't need to consider, but this one you do need to consider. So when you consider momentum, you need phonon help. When phonon is a very lazy particle, it's very slow. Give example like for compound semiconductor, for carrier lifetime is in picosecond, even slow one is in nanosecond. But for phonons is in millisecond, it's very slow, make difficult to make any emitters. So it's a challenge, but doesn't mean we will give up. Actually, we are academic, we always try about that. So this one is about 15 years ago. Actually, the first CW laser made by Intel at 2005 used some silicon Roma properties. I don't want to go through the detailed physics, but what they did is they use laser pump material to get laser. The bigger problem for this one, guys, is we need electronically pumped laser, but it's an optical pump. That's in the big step. So far, they still don't achieve that. But even like this, guys, actually the paper was published 2005 in Nature, and they make big news. So another big news recently is at 2012, is from MIT. So they use germanium and other group of materials, they made a laser. So when this was published, guys, also big news. For first year, the citation over 100 times. It's very unusual for photonics area, especially for traditional photonics areas, have so high citation. The bigger problem for this one, guys, is this you have very high threshold and the power is too low. Still long way to go to achieve any practical laser. Another new material that come out, this one also is from 2015, and this year they published another new paper. So this one also optically pumped laser and use tin. Tin is a new kind of metal, put in germanium, you potentially get direct bandgap, and you can get optical laser. This laser, guys, only laser at 90 Kelvin, optically pumped, because of fundamental limitation, they even published in Nature Photonics. So if group 4 materials cannot do it, what we can do with other materials? So basically, we have a compound semiconductor. We can put the two materials together, and somehow, like a glue, if we can bond together, we will make it work. So I have to say, I admire the Japanese colleagues. They try very hard from 1980s until now. So they get room temperature electric pump laser, but their lifetime is only 200 hours. That means if you have a device, only have 10 days to be used. Another result come out of this year, actually from Montpellier, a friend group, they use antimony. Gallium antimony is a very soft materials. You potentially can put on silicon, you produce some dislocation, majority in the interface, but you still have some defects across the whole wafer. So somehow the group managed their problem. They get laser up to 80 degrees, but you still need a lifetime. I will talk about it later. But in the meantime, you still need get the telecom wavelengths. So another approach, if we cannot get gross materials, can we just like a glue bonding on that? So the more successful group is from Santa Barbara, and they work in the area for more than 20 years. And also Intel or even Huawei, a lot of companies claim they have this technology matured. But the bigger problem for this one is bonding technology, the yield is very low, and they do have problem for massive production. So what's our technology? So our technology called 3-5 quantum dots. So we have a 3-5 quantum dot. That means you have a direct function of density states. If you have direct density states, you have very low threshold current density, and also you have stable room temperature application. So I have a video here. I show you see how do we do this quantum dot growth. So basically, grow in the mass and gallium arsenide, you have formed 3D confinement like a yellow beans on the surface. After that, you grow layer by layer and cover it. Eventually, you will get a quantum dots. After that, you put it on gallium arsenide, you put in device. So that's some nice picture I made in last 20 years with different size quantum dots. It's more like a yellow beans put on surface, but use a MB ultra high vacuum facility. So why we need the quantum dots? So a summary last few years results. First thing is temperature independent operation. That's a conventional indium phosphide laser. You can see from -40 to 85 degrees, the drawer current need to get bigger and big. But for quantum dots, the drawer current from -40 to 100 almost the same. Another thing is high temperature operation. So for quantum dots, because of quantum confinement, the property of quantum dots, they can get 220 degrees. That's way high than conventional device, and also you get a very good lifetime. It's 5,000 hours, almost no degradation. Another thing is our recent results. We compared the quantum dots and quantum well device. You can see for quantum dots work very well with a good wavelength and with laser up to 105 degrees and CW to 865. But for quantum well, we pump very high, never get laser. We work with Cambridge University colleagues there. So we use model predict for quantum dot laser. If you have a defect density 310 to 8 per centimeter squared, you still get a possible laser. But for quantum well, if you get a 710 to 7 multiply 10 to 6 per centimeter squared, you almost no possible get a laser. So the reason is, for putting in simple term, for quantum well, if you have a carriers, easy to move into defects because it's more like you work on flat surface. But for quantum dots, because of quantum confinement, you carry need to jump out between is nothing there. So it's more like from the first floor to second floor. So the carry in the first floor, the defects in second floor. So you need a carry jump from the second floor, first floor to second floor, but there's no stairs. So that means limited the carrier to the defects to make it more efficient. Another thing, we predict a long time ago at the 2008, if you have a defect cross quantum well, that means carrier easily to be there and generate heat and generate more defects and get the device to be killed. But if you cross one quantum dots here, so you will only kill 1 or 2 of you, the majority quantum dots still work. That's why if you have working quantum dots, you will have much longer lifetime, have potential applications. So simple summary here, for quantum dots, you can easily get a laser with a defect environment, and you get a much longer lifetime, produce practical device. So I simply summarize the last few years, what we did with the roadmap. At the 2007, I joined UCL. And actually my first paper after set up the lab taken me like more than 3 years. The first video came out in 2011. So we predict, using the simple model predict quantum dot laser can be much easier laser at group 4 materials. So the first thing is we do the growth. I don't want to go through details, but we get the first CW laser on germanium in other group 4 materials, and also the CW laser over 60 degrees in very important telecom laser 1.3 micron, time wavelength 1.3 micron. So this paper actually, we claim we can build up the bridge between group 4 and the 3-5 materials, make a silicon photonics laser work. So after that, the next year, guys, actually we use the materials from, in same year, we also grow gallium arsenide on silicon, actually directly, not on germanium. We also get a quantum dot laser at 1.3 micron, but it's only post condition. So at the 2012, we build up on first our germanium idea. We put the germanium on silicon, we put the 3-5 on germanium again, made a laser. We get the first CW laser in the world, and we get a laser up to 84 degrees. Actually, at that time, every time I give UI talk around the world, actually I get a lot of challenge. They claim why, is anybody believe the dead area, why you achieve it, what's the reason you get it. I really appreciate Professor John Barber's group at Santa Barbara. The first thing I got to say, Professor Barber's group is the leading group in wafer bonding on silicon photonic lasers. And also they use our method, use on ground germanium silicon substrate. They get better results than us. They get 110 degree CW and the yield is much higher. In their paper, they claim their laser with our method is much better than their bonding results. So at 2016, that's another biggest breakthrough in the area. So basically, we get CW laser, the working laser, no problem. Do you have any lifetime? For any electronic or photonic device, if you don't have a lifetime, that be meaningless. So what's the results we got is we produce the growth, better quality, get very low defects, and we get over 100 milliwatt room temperature power, and also we get CW at 75 degree. I have to say, guys, because our fabrication is limited by our measurements setup, and we measure the lifetime of the device at 3,100 hours. So when it's finished, we use modeling predicts this laser will over 100,000 hour lifetime. So that means, so this device, even with a very basic, UCL very basic fabrication lab, we can make a laser over 2 years. That means, guys, this laser is good enough for your mobile phones. Because if you continue working for 2 years, for you use your mobile phones or this kind of consumer electronics, you need 2 or 3 years lifetime is more than enough. So this device is more than enough. So it's a big step for the area. The paper made a feature article for Nature Photonics, and in the last 4 years, entry the paper every year starting over 100 times, and also it's the third in the 2016 rank Nature Photonics papers. I got to say it's a conventional device. We work in engineering. It's not very common. We have a high citation paper in very high impact journals. So after that, actually Professor John Barber who made another good progress. They make their device much longer lifetime. Laser on silicon, they have over 342 years lifetime. That means there's no problem for any potential application with this method. But also they made a very high speed. They get 12.5 gigabits. And we work with the Chinese colleague in Zhongshan University. We made the first laser bar array over 100 nanometer range. That means our laser, we don't need the individual laser bar, but we can have one laser array from one wafer and cover all the broad multi-wavelength communication channels. And also we did the first time with narrow range, also with Zhongshan University and the Semiconductor Institute. And we get the narrow bar device. We get a laser over 125 degree, and we get a very low noise. The noise is about 156 dB per hertz. And all the threshold guys following the the history, that double hedge structure, that's a quantum well laser. So that's a quantum dots and the quantum dots laser on silicon. You can see a concentrate quantum dots laser is close to the commercial application, is compared to the best results in the commercial market. Any other important results I think is from Professor John Barber group. So what they did is basically to say if you use a quantum dot laser for optical connectors, you don't need an optical isolator. Actually, optical isolator is a big part of photonic inter circuits that will reduce the cost dramatically. So for this year and last year, we work with the Chinese University, Chinese Hong Kong University in Shenzhen. We get small lasers because guys, I told the second challenge, we do need work with the CMOS, you need nano lasers. So we get a very small lasers, micro disc, and we also get a photon crystal laser on all materials. The results is pretty good and initial step, but it have a very promising future. So basically guys, I think my time almost finished. A summary what we did. So 2011, we made the idea, we proposed the idea, we made for the laser. 2012, we make the first CW laser. 2014, Santa Barbara follow a step. And 2016, we make the first practical laser. And 18, Santa Barbara also follow step. They push for the step. I have to say, at 2018 also made a very broad laser range and also high gain. At 2018, Santa Barbara realized the we don't need the optic oscillator with the silicon quantum dot laser. And in the meantime, at last year, Santa Barbara spin off their companies. So I put here, that's the two results from us. And so from photonic laser and the magnetic laser. So I predict we will get over commercial laser for quantum dot laser at this year, as last year. Unfortunately, guys, we all know we want 2020 to be restart because most time this year I have to stay at home so far. I don't think we can make any progress on commercialization. In the meantime, so also we get a big round for integration with the Cambridge, Southampton, and Cardiff for photonic inter circuits. I predict 7 years later, we roughly will get the IPC interphotonic circuits ready for silicon chips. Finally, I would thank you and thank my group for their hard work to do at UCL to support this activity. Thank you very much.
Oh, thank you, Professor Liu, for your talk. And I think we all agree we want to, if we have the chance, we will try to start the year. But since we're here now, we'll just try our best and cope with the situation. Now let's move on to the Q&A session. So I have a question here. So which heterogeneous integration techniques we can commercialize used to fabric large-scale active photonic components in the next decade? By epitaxy or transfer printing or wafer bonding?
I think it's a still argument there. I think all the technology have their purpose, but for massive production, you depend which technology you go. Let's say wafer or transfer printing or wafer bonding. Guys, you can understand one thing. So even for laser, indium phosphide telecom laser, the yield is less than 40%. So even you put a whole wafer in your silicon wafer, but you have a 60% laser doesn't work properly. So that's a very limit. Your after bonding, the yield gets much smaller. So that's a very limited any potential application because indium phosphide material self for on silicon. So I don't think, in my opinion, wafer bonding or transfer printing can be massive production for laser. Especially for high density laser, we need for data centers or telecom communications. Having said that, but I do think the technology can be used for solar cells, because for solar cells, you don't need high density device, or you can just easily bonding. The bonding can easily even somehow not very strong, so you can work. I wouldn't say any technology not useful, but I think for laser, especially high density laser for telecom or data center application has to be epitaxy growth.
Okay, thank you very much for that answer. And I had another question here from Zichen. He asked, so you mentioned the 3.5 laser of your work and the germanium/silicon laser. Could you please compare them? He said he knows that the epitaxial 3.5 laser on silicon is still the mainstream. What is the reason behind it?
The reason is, guys, if you grow gallium arsenide direct on silicon, you have two challenges. One challenge is the lattice mismatch between different lattice. Another challenge is the phase difference, because the silicon is a next neighbor the silicon. For compound semiconductor, say gallium arsenide, next neighbor gallium, next neighbor is arsenic. So you grow gallium arsenide on silicon, you have a problem with mismatch and phase difference. But if you grow germanium on silicon first, you are dealing with the lattice mismatch problem. When you grow 3.5 on silicon again, actually you're only dealing with the phase problem. So you just step by step, make your life much easier. That's so far germanium on silicon device still better than direct ground silicon. But for long term, maybe it doesn't matter with developed technology, but these two, I wouldn't think get rid of any one of them. But I do think germanium ground silicon can be very, can be very promising because they can get the defect very, very small, make the growth much easier. And also for the long-term application, for the yield can be much higher to produce the laser.
Okay, thank you, Professor. Due to time constraint, we'll have one last question. This is from Xiao Boyu. His question is, for data center applications, will the 1.3 micron work okay, or wavelength conversion is needed?
Oh, I don't think you need a wavelength conversion, guys. The reason is for 1.55 micron is for long haul applications, like from China to UK, China to US, because then the loss is lower. But for 1.3 micron, mainly is for application called local area, like in city, like in London. So that we use 1.3 micron laser. So for data center, your diameter is about 3 kilometers. So the way smaller than big city like a 10 kilometer range. Another thing I got to say, even nowadays for the data center use wavelength communication, they even use 850 nanometer laser because the loss not a big problem. So 1.3 micron for data center is more than enough.
Actually, we might be able to have one last question. So the question is, Professor, do you think carbon-based semiconductor materials can challenge silicon-based semiconductors in the long term? For example, in physical limitation.
Really, guys, I'm an engineer, guys. I'm not a physics guys. I would like, from an engineer point of view, anything, if you want to put a silicon, you need a compatible with silicon. Even 3.5, we still cannot put a 4 line in the second line, will become the bank line. So for carbon, we have a lot of study. I personally believe it's very difficult. You think all the 3 nanometer, 5 nanometer, or even 7 nanometer CMOS line, how much it costs? It's not about the science, it's about the company. Do they want to change? If the company wants to change, you need a way cheaper, way better technology. So far, guys, we need a silicon substrate. Silicon substrate is massive. Nowadays, they have a 13-inch capacity. But for carbon, it's very challenging to get that kind of wafer. Another thing is for silicon technology, you have very good oxide layer, silicon dioxide. The reason is, guys, for 3.5, I give you tell a story, right? When I did my PhD, I believe gallium arsenide and compound semiconductor will replace silicon in 10 years' time. But actually, silicon technology march on, get better and better. I personally believe anything you want to have a commercial price, you got to build up on silicon, got to be compatible with silicon. If not, it's very difficult to have any meaningful application. Actually, carbon, oxygen, somehow is the bigger contamination for silicon fab. That's something we definitely avoid. So I have my doubt on this, but it's science. I'm an academic. I'm open for this.
All right, thank you very much, Professor Liu, for your time. And that should conclude our morning session. And hopefully we'll see you again in the near future.
Thank you very much for having me here. Thank you, guys.
Okay. So, hey guys, that concludes the morning keynote session of our event today. And we'll proceed to the symposium, and details are here. And see you guys there. Thank you for joining us. Professor Wang?
Hello?
Yeah, we can hear you.
Okay, can you hear me? Okay. So should be no problem, right? Let me, when should I share the screen?
Give me one
Still have
second.
20 minutes. I'll be online. You can call me. I just in and out to get some water. So
Yeah, I'll do the introduction first, and then I'll
okay,
allow you.
okay.
Yeah, I'll give you.
So I'll mute the voice and all the audio and also stop the video. So right, okay. So I'm online.
Okay, thank you. See you in a bit.
Okay, very good. Thank you.
Okay, the second half of our event will be started in 5 minutes. Yes, Professor Yang, can you talk now? Oh.
Okay.
Okay, Professor Yang?
Yeah, online.
Oh, sorry, I'm talking to our second
The other one.
speaker.
Okay.
Yeah, sorry.
Okay.
Okay, we'll do the testing later. Let's see. Okay, let's get started. Welcome back, everyone. Good afternoon, good evening, good morning again, depending on where you're tuning in from the world. Welcome to the second half of the first Cambridge International Young Scientists Forum, the Emerging Technologies for the Next Decade. We're very honored to have the first keynote speaker of the second half here with us, Professor Wang Zhongling, who is a Height Tower Chair in Material Science and Technology, Material Science and Engineering and Regents Professor at Georgia Tech, and the founding director of the Beijing Institute of Nano Energy and Nanosystems. Dr. Wang pioneered nano generators from fundamental science to technological applications. His research on self-powered nanosystem studies has inspired the worldwide effort in academia and industry for studying energy for micro nanosystems. He coined and pioneered the fields of piezotronics and piezophototronics for the third generation semiconductors. Dr. Wang is ranked number 15 among 100,000 scientists across all fields worldwide. His Google Scholar citation is over 235,000 with an H index over 239. Dr. Wang has received the Celsius Lecture Laureate of Uppsala University, Sweden, the Albert Einstein World Award of Science, Niels Planck Lecture Award, BNI Award in Energy Frontiers, Global Nano Energy Prize from the NASMAT Society UK, Distinguished Research Award from Pan Wenyuan Foundation, Distinguished Scientist Award from the US Southeastern Universities Research Association, the Thomas Rauter Citation Laureate in Physics, World Technology Award in Materials, Distinguished Professor Award, which is the highest faculty honor at Georgia Tech. And he's also received NanoSmat Prize UK, the James C. McGrody Prize in New Materials from American Physical Society, and MRS Medal from the Materials Research Society. Dr. Wang was also elected as a foreign member of the Chinese Academy of Sciences, a member of European Academy of Sciences, academician of Academia of Sinica, International Fellow of Canadian Academy of Engineering, foreign member of Korean Academy of Science and Technology, a fellow of American Physical Society, a fellow of AAAS, fellow of Material Research Society, a fellow of Microscopy Society of America. And he's also elected as fellow of World Innovation Foundation and fellow of Royal Society of Chemistry. And Dr. Wang is also the founding editor and chief editor of the international journal Nano Energy, which has an impact factor of 15.5. Ooh, that was a long introduction. Now, without further ado, I'll give the stage to Dr. Wang. Please proceed.
Thank you very much. Let me share the screen first. Okay, share. Okay.
Okay, good.
Can you see the screen?
Yes.
Okay. Okay, first, I'm very pleased to give this talk to the Cambridge International Young Scientists Forum. And I was a research fellow at Cambridge back to 1988 to 1989. So I spent 1 year at Cambridge as a young research fellow. So I'm very happy to talk here about our recent research on energy and the sensors. Okay, so in the last 20 years, we devoted a lot of effort for smaller energy. What do we mean by smaller energy? So in our energies driving our society advances, many key technology rely on energy, from the traditional coal to the oil, and which is the driving force for all the technology we use today. As we move on to the future, we enter to the different stage of our life, our society's life. For example, like Internet of Things, nanotechnology, artificial intelligence. We face new challenges. So what are the new challenges for energy? Not only the energy, total amount of energy available, but also the way the energy being utilized. Our traditional society use the energy, for example, is use the power grid. You can deliver powers to a variety of utilities, homes, factory, etc. We also use the storage units for portable electronics. Those are the two main forms of how the energy being delivered. But can this solve all of the problem? Well, most of the problem, not all the problem. So the new future we face in is based on a cell phone platform. We have a lot of gadgets. For example, we have a lot of handheld electronics. We want to monitor a lot of things. So we have the data, big data. We want to know the positioning, velocity, speed, at whatever, the weight, everything we are moving around us. So we want to be tracking. So as the world advances, we face new challenges. Distributed, smaller, large number of units, which requires mobile power. So it changed the way we look at the power. For example, traditionally look at the power plant, we deliver the home, use cables for power. But now we face the new challenge is that smaller units are huge number. So our energy utilization from ordered or constrained energy to distributed and disordered energy, from cable wired to wireless. So therefore, the energy we talk about is not only just how much power generate, it's about the way the energy being utilized in our near future. So we call this like the entropy in energy distribution, is to get more and more random, wider distributed and smaller units, but the number is very huge. So how do we solve this problem in near our society? And but this is about 2005, 15 years ago, we raised the idea called solar powered system. Can we use the energy harvested from our environment to solve the energy which we require for Internet of Things, for many technologies? So when I phrased this one, for the last 15 years, we devoted a lot of effort to develop this kind of technology. So I'll present you some of the research we have done in recent years. The technology I introduced today is called triboelectric nanogenerator. So how does it work? The way it works is two dielectric medium physical contact. You have the surface charges here. So when you have the surface charge, you build an electric field across two medium. So you change the gap distance, or you change the capacitance. There's a current flow from one electrode to the other one. So this is the way we be utilized for generate power. So let me ask the demonstration this here. Tapping here, okay, tapping here, and generate a little power over here. So this is called triboelectric nanogenerator, and there's fundamentals related to this one, and how the power being delivered, how the charge being created, and how much we can get from here. So what's the advantage compared to what we have? So let me show you this one. Okay, the first one, this is the traditional electromagnetic generator, very powerful, very is a key technology for power today. And this is our TNG, triboelectric nanogenerator. You can see two have different modes and work in different ways. Let me show you the difference of the two. Okay, is maybe a little noisy. You can see this one. This is the electromagnetic generator. It runs at a faster pace. This is the TNG. Okay, it can run slow pace and still let me cut it off a little bit. You see, this has run a fast pace, but the output voltage is still low, can drive a couple of lights. But this one run at low pace, the output voltage is so high, you can drive many lights simultaneously. So the key difference is here. The traditional technology at low frequency have very low efficiency. So it's only be utilized at a higher frequency. So when the frequency is so low, it is almost useless for power generation. But our technology at low frequency has a much more advantage compared to traditional technology. So in a frequency range in our daily life, this have a unique, unbeatable, uncompatible advantage. So let me show you this one. So this is the base here. Let me show you the physics here. You say, well, you call trouble nano generator. The trouble electricity is well known. What's new here? Trouble electricity in the science called contact electrification. It has been known for a long time. But how does the trouble electricity generated is not clear until very recently. And if you have a plastic rod, rubber on an animal fur, you get an animal fur get a positive charge, plastic rod get a negative charge. So how come the charge being segregated according to different materials? So this is a remaining physics problem which has been around around us for a very long time. Even this phenomenon is well known, but we have to explain it very well by this. So we devote a lot of effort, say how the charge being created here. Different materials have different charge. So let me just very briefly show you here. Okay, because all the materials, papers, fur, wood, whatever they have trouble electricity, it's not just crystal. So we propose a model, use the interatomic electron transition model to explain the charge. Let's say this is one of the atom belong to A materials. This is one of the atom belong to B materials. If the two separate a little distance, there's no electron exchange. But if you push them further closer, the barrier between two, the potential barrier between two becomes lower. In such a case, electron can transfer from one atom to the other one. So as we have an animation, you can see this one. Let me see. You can see, let me put this small. Okay. You can see this is the one atom, the other one. If you push them closer, then the barrier between two drops. So the barrier low enough allows electron transfer from one to the other. And then in such a case, then the electron will be kept over here. Okay. So this is the model we proposed to explain the trouble electricity. Okay. So this is the basic model. When you talk about trouble electricity, is a key type of contact electrification in which certain materials become electrically charged after they become physical contact. Our new understanding is the contact electrification is a quantum mechanical electron transfer process that occurs for any materials in any states, in any application environment, even up to 400 degrees C. So we do some measurement to show that this case. So the charge, how the charge being created, we know that. The second one, how the charge flow. For example, how the charge flow from one to the other case. And the traditional technology utilize the electromagnetic inductor. So therefore, when your metal rod cut the magnetic flux, the current flow through the magnetic metal rod to create current. This is called the conduction current. But now, in our case, we have a very different case. This is called a displacement current. Displacement current is built in Maxwell's equations here, so which was first proposed in 1861 by Maxwell. So if you have the displacement current, and what his definition is that displacement current is not a current due to flow charge, but a time variation electric field. He's talking about the electromagnetic wave that time. So basically, this is the standard form for that. But now this is the medium polarization. The polarization due to the electric field induced medium polarization. It does not include, okay, let me see. It does not include the polarization due to surface charge due to the trouble electricity. So therefore, in such case, such a charge can create additional term here. So we need to introduce this additional term into the Maxwell's equations here. So to be simple, you can see this is the displacement vector, and this is the medium polarization term here. Just like you have a charge here, the medium polarized according to the distributed field in a space. But now if you have a trouble electricity here, we have the charge over here. The existence of those charges create additional charges on the surfaces here. And this gives additional polarization term, which even will remain even you retract electric field from this charge here. So therefore this term should be there. So we add one more term in a displacement vector. So therefore, so besides the classical definition, we add another term here. And this term, if you substitute this displacement vector into this equation here, you can get a new form of equation here. You substitute here and here, and then you get a new form of equation here. So you can redefine the space charge density, the current density, include additional term, then the Maxwell equation return to its original shape as it was, but except some of the term have slightly different definition. So we introduce the displacement current due to the electrostatic charge on the surfaces into the equation. From here, we can derive the output of the TNG quantitatively. So therefore, we expand the Maxwell equation into such a system. So the first term here, basically this term is represent electromagnetic wave. The second term is the power generation due to the surface electrostatic charges when you change the shape of the deformation of the medium size, medium shape. Okay, so if you look at this one, is basically this is the conduction current, this is the displacement current. So therefore, this is the time derivative of the magnetic flux. This is the time derivative of the surface triboelectric charge or piezoelectric charge. So which represent the principle of nanogenerators. Then we call nanogenerator because when we first introduced this one back in 2005, we have the term due to nanowires. But here we utilize the displacement current as a driving force. So therefore, nanogenerator is a field that utilizes displacement current as the driving force for effective converting mechanical energy into electric power. So therefore, there's two general terms. So this is representation of the displacement current over here, and this is what we add in the equation. So if you have this one, basically, if you have a displacement current, you have the first term due to medium polarization, which gives electromagnetic wave for the electromagnetic, the Maxwell equation. So if you add the second term, we add it in, which is the foundation output current, and voltage can be derived from this term, which give you the output power characteristic of the nanogenerators. So we worked this out in the last few years. So these two terms normally are independent because these have a rather low frequency, these have a high frequency, so they don't couple with each other. But if you have the mechanical tricking, the frequency goes high, both could be coupled at some frequency, but due to the large difference in the frequency, we can treat them independently as of now. So this is the term. As you can extrapolate Maxwell equation to new forms, which include both into the entire equation here. Okay, so this is what we theoretically developed here. Okay, now let me show you the applications. So you say you have this so many fundamentals. What applications? Let me show you. First one, let's say as small powers. So this is example. If you have this tubular, very smaller rubber made tubular structure here, which have our TNG built in here. In such a case, you can put in the shoe insole here. As a person simple walking can give you small power here. So this allows to driving small electronics by human motions, by anything tricking in our environment. So this is the demonstration shows that for the this is the cell powder electronic paper. The electronic paper can be driven here. So this, the cheapest materials is paper. Okay. So therefore, you can use paper make triboelectric materials to fabricate here. Let me show you. This thing is give you the e-paper driven by TNG. Okay. So you can see here. This is the paper here. Here, this is the TNG. You can see that drive the color change of the e-paper. Okay, because the output of voltage of the TNG is large, so you can use the small physical motion to that, and you can change red color into different colors, green colors, and other colors. All this one can be driven by this. Okay, and you can also do this one by for others purposes, multicolor papers for that. So basically, a small motion, you can change the color of different objects per your wish. Okay, so per wish. So this is basically a paper-based device here. The other one is that you can simply choose the materials which have a different mechanical electronic property for it. You can choose silicon as the materials which has a flexible, stretchable materials here, and you can twist this multiple times here and give you a power like that. Okay, you can see. You can put this on a shape adaptable objects or arms here. You can tap in different parts. You can get a signal out over here. This is basically a very good illustration for robotics. You can make a robotic to be smart, and you can also be on the you put on the floor a person free walking can generate a couple of watts of power. So therefore, any free motion, any energy wasted on the environment can be effectively harvested. Use this technology. Medical. We have a lot of advanced medical devices, but without electric power, and this won't work. So therefore, one typical example is the pacemaker here. So you can see we use the breathing of a small animal. We can drive a simulated pacemaker to work. And last year, we made a gigantic progress in this one after 10 years of hard working on solar-powered implantable medical devices here. I'm sorry, this is a little, you can implant this TNG inside the body, can generate sufficient power and sensors for a variety of purposes you'll be interested in. So this was last year's work. We'll be able to use this TNG to use the breathing of this pig to harvest about half microjoule of energy, which is sufficient for the energy required for a pacemaker. So I think this is a landmark work because we have been working this for a long time. For the first time, we can achieve solar-powered implantable medical devices here. We can also do drug delivery. For example, we can use TNG or body motion to generate a voltage. We can drive the infiltration of the drug into the skins here. So this is with use of our TNG. Without use TNG, the rate at which the drug is being delivered can be different by a factor of 5 or so. So therefore, you don't need to cost very much, but you use this one for the power. Fabric. Fabric here. Fabric is a very typical example of any material you can use. For example, you can have a fibers-based one. But how can be fiber-based to be a power generator or to be a sensor pad? So you can do this one, use the sliding of the fibers between one to the other one. You could be a power source for that. Okay, so this provides a new research direction for people working on the textile industry and the fiber engineering here. And you can make this one to multi-metrics, then can be for sensor purposes here. Raindrop, 2014, we show for the first time that a raindrop hit electrode here. This electrode encapsulated with the dielectric materials here. You can generate power. So there time we'll be able to generate a small power by this. And in such a case, you could. You can see this right here. You can see that, right? So this is the raindrop, and we use this one. We start this one very recently a lot more because it's not only for power generation, but more important study the interaction of liquid with solid interfaces through this one. But in any case, here I just show a small power. TNG can also be driving a model, not only a power generator but a model. You can drive electrostatic model. You can drive flow at a high speed. You can see here is TNG here, and this is the model here. You can try the TNG slide once, slow pace. But here, this runs at 1300 round per minute. So this is a good way to illustrate. We can use this as a model-driven or as an actuator. And not only do that, we work also on energy storage. Let me make sure this is clear. So we convert random irregular motion energy exists around us into electric power through our TNG technology. But in the middle here, we have to have a power manager because the output, this one, usually have a high voltage but lower current. So we make this power to be regulated, to be utilized for electronics. So we make this one into a self-charging power units, self-charging power unit. So power generation, power management, and power storage for further utilization. So we call it self-charging power unit. We work on all of them. We work on 3 parts of them to make a completely unique package for our application in a very different field. Let me show you this one. This is a power management circuit. You can see this is the TNG. This is a power management circuit. You can regulate the energy to make it useful for a variety of purposes. This is the TNG. This is the contact separation mode, and this is power management system. And this is the one you can utilize this one for other purposes. Because we make a irregular energy into a regular utilization. You can also use wind. When you talk about wind energy generation, people always talk about the turbine engine here. But here we use the polymer, like a tongue structure. When the wind goes through here, this tongue oscillates resonance. You can get a little power. You can see this one. You blow this one. This is just making this tongue oscillating. And we recently integrate this into different units here. And a unit can be added up constructively, so we can use one to power a sensor system. For carbon monoxide sensors, utilize this one, use at a radio frequency, and we can send a signal to a couple of kilometers away once every 10 to 20 minutes or so. So this is making it possible to be distributed self-powered environmental monitoring for water quality tracking, for atmosphere monitoring, as well as fire protection. So this can be a very useful self-power system, as we illustrated here. Okay, so this is the one we can utilize this one for floating waters, and you can also prevent natural disasters, for example, landsliding or any kind of this kind of work from river flowing here. So you can do a distributed environmental monitoring, use our approach, and this is very good. You can save a lot of human power need for this. You can also be collect a lot more data than used to be. So I think this can be a very good system to look at that. The second one is solar power sensors. TNG is not only just a power generation, it's converting mechanical triggering into electric signals. So let me show you. This is the ping pong table, and the ping pong table on the top rim and the side edge here, the top edge, side edge, and you can validable and invalidable. So when you put the TNG on the top edge, the side edge, you can detect a signal, and which you can detect this is a validable, this is a validable or invalidable, just based on the rule of the game. So this is convert a mechanical triggering into an electric signal, so it can serve as a solar power sensors, a sensor that does not need power, but give you electric signal once being triggered. Okay, so this can be very useful for smart spots here. For keyboard, we can work on a keyboard. When you type in the keyboard, we can be utilized to recognize the way you typing. You can input the password, but the way you is different from the one which the machine knows. You may not get into the system because the machine not only recognize the password, but also recognize the way you input the password. So we put this one into a system that we can demonstrate for effective recognition of who input the signal. You can see we have 6 digits here. We have 6 digits here. This is my student Changsheng Wu put it in. He put a 6 digits in, and they can identify, yes, Changsheng, you put it in. So therefore, the machine learning help us this big data, so we can do the the identification of individuals at accuracy almost 99%. So this is the keyboard idea here. If you go to the library, you have 100,000 books. Tracking those books can be tremendously human power consuming. So we can build our things under the book, inside the book. Anybody touch this book, you have a signal generated. Let me show you this. You see, someone move it here. This is the receiver, and the signal transmit to this receiver wirelessly. Just use the power generated by the motion this person move the book. You can also put this one in a different line of different page of book. You can track in those documentations here. You can also make a soft robotics for handling or grabbing of soft materials by such a design. Okay, let me turn it off. So this is have a diverse application for documentation tracking, because if you have a battery-driven system, it plays there. If nobody touch it, and it is be active for some time, then the power will be gone. So therefore, power sensors in many cases have its own unique. So this is a health monitor. You can put it here, monitoring the pulse of a person. You can also even derive the blood pressure based on the signal we received here. So this technology is close to be commercialized for pulse detection. Yeah. Okay. So this is the paper-made TNG as a microphone. You can put into the ear of this robot, so the robots can record the voice, the music you input in, and also can identify what are who input the music. Let me show you here. Okay, the first one is I hope you can hear. This is the original music, original music playing. Then we use this paper-based TNG, record it. Then we play it back. Okay, let me just go this a little fast. This is a playback, no digital filtering, no data processing, just original voice after recorded plays back. So we preserve 90% of the accuracy. And we also can use this as a robotics communication skills here. So you can, the robots can recognize who is talking. Okay, let me show you this part. Okay. The lady says, "Hello, Harry," and see what the robots can recognize her or not. The robots cannot recognize her, okay, because the original voice. This is Henry, and he's coming, and see what the robot says. See, the robot can recognize the second person, so therefore be a voice recognition application. Lastly, I'll talk a little bit about the blue energy. This is a large scale energy the proposal for that. So you know the most energy around the coast area use the ocean here, but have such energy is tremendous difficult because class technology have a corrosion problem, low frequency, and difficulty to operate, and high cost, and also the efficiency is rather low. So even we have this, as I explained at the beginning, that TNG has the uncompatible advantage of working much more efficient at low frequency. So how do we use TNG to collect the energy from water wave, from light wind? So we came this idea, I proposed this idea in 2014. Then is that we utilize is a sphere, and we have another sphere inside. So in a water environment, the inner side ball rolls back and forth, for example, like this. The power will be out. In such a case, if the contact electrification between the ball and dielectric medium change the symmetry of the charge on two electrons, so when the ball rolls back and forth, the electron flows back and forth across load, which is the way output of power. This idea appears simple, but it works in the water. And recently, we can also amplify the frequency of the operation, because the water wave have a low frequency. So we use this pendulum structure here. The water wave structure once, it can last for 80 seconds for power harvesting, for example, like this. And so this is amplify the frequency in our environment for truly high efficient energy harvesting. And this one make our large improve the TNG output in the water environment, even light wind. You know, in such a light wind, the traditional technology cannot be used at all. It's too low. If you have a wind speed lower than 3.5 meters, this turbine engine won't work. And so therefore, in our case, we can use like low pace movement. So how do it work? So we put it in the ocean, regardless depths, regardless the low frequency. So we could make this one use the water motion here. So how do we do that? We propose, for example, we make a networking on the surfaces of the water. So this is floating, and you can make this water not a one layer, but multiple layers inside the system, and you can make this truly networking for collection powers. So we recently have made this really a good output so towards our dream for large scale energy harvesting. And if we could do this at a low cost, long lasting, safe way, and operate a different environment, this can be a new approach for solve the energy problem over large. Okay, so what's the big advantage? The big advantage is that compared with classical technology, we have magnets, coils, and output the power is the square of the frequency, but utilize heavy materials here, metal materials here. But our TNG use organic materials, the output power is linearly dependent on frequency. Why? Because the output voltage is the independent frequency of the operation. So in such a case, you can see at low frequency, this is a few hertz, the EMG cannot output anything, but our TNG can output a large power of this one. So in such a low frequency, we have uncompatible advantage compared to classical technology. So therefore, this is why we are confident this will be very useful, because we can do something that classical technology cannot do. So at a high frequency, you can use the classical technology, a low frequency use ours. So therefore, both can be used in a way complementary. Okay, so if you see this one, we make this one into the water tank. You see this, the water tank. Okay, this water tank here floating. Okay, and this the dancing in the water sort of dynamics here in a water track like that, or track like that. So in such a case, you can be utilized for effective energy harvesting. So this is just still at an early phase. We are working very hard on this. Okay, so over large area of surface of Earth is being covered by water, but energy offered by this hardly being utilized in any way. So we propose this blue energy idea. So hopefully one day we can bring this one to benefit humankind around the world. So we call blue energy dream. Okay, it's blue energy dream. So today I just very briefly, due to a lot of time limitation, I'll give you a short talk. Mostly I cover the fundamental science of contact electrification, because contact electrification has been known for a very long time, but the scientific understanding remains cumbersome for years. So until recently, so a lot of new data shows that it is electron transfer and how the electron transfer here. So was the first question. The second question is the Maxwell's dispersion current. We modify the term so we include that due to the medium polarization term, the surface dielectric, the surface charge term, which induces a medium polarization into the Maxwell dispersion current. So we expand the Maxwell equations into a new form for this. So we use this one, we can derive the output quantitatively. So I can see these two as the fundamental scientific part. Then we demonstrate very quickly for TNG as a micro nano power source, as a solar power sensors, and also can be used for large scale blue energy. And we also have another application, which is for high voltage, right? So I will not use such an opportunity to do time limitation to talk about this one. We also have some opportunity for commercialization. So look at the forward is micro nano power source, solar power sensors. I think this will come first for commercial application, then the blue energy and the high voltage source. This is we view as the future direction here. So I'd like to thank our team for years' work, which solve some of the, not only the fundamental problem, but I'll demonstrate this could be a potentially very important technology for the world in the near future. So I'd like to thank the conference organizers giving me this opportunity. Hopefully my talks be informative and useful. Thank you very much.
Well, thank you, Professor Wang, for the very inspirational and I would say mind-blowing talk there. Now we should have time for maybe 2 quick questions.
Okay.
Now from the chat. So the first one is Professor Wang, what is the maximum conversion efficiency of TNG?
TNG, okay, very good question. Oops. If you do the just consider one trigger, we measure that we can reach efficiency 50% and above. And because if you trigger as a lower frequency, we can get that kind of efficiency. So efficiency is very high. In the water, in the water, if you have the water wave and the water striking on the device, we can have an energy conversion efficiency about 28%. 28%. So you can see the efficient point of view is rather very exciting. So that's why I believe this one can be useful in many ways.
Okay, thank you. And second question, Professor Wang, is your nano electric generators insensitive to any EM interference? Is external EM fields impose additional difficulties for your power regulation units?
Okay, a very good question, because we do not utilize magnets or magnetic material for power generation, because traditional technologies, magnets, coils, permanent magnets. So there's and also the sensitive to electromagnetic interference here. Ours is not. Ours is not sensitive to any electromagnetic interference or any kind of magnet materials around it. So it won't affect that.
Okay, so due to time constraint, I think we'll stop for now. And thank you very much again, Professor Wang, for joining us today. And hopefully we'll see you again in our near future events. Thank you.
Thank you for the invitation. I wish you have a very successful symposium and everybody enjoy the next few talks. Thank you.
Okay, thank you. Okay, now we're going to move on to the second keynote speaker of this afternoon. Please allow me to introduce you, Professor Yang Guangzhong, the founding dean of the Institute of Medical Robotics at Shanghai Jiao Tong University. He is also the co-founder and was the director of the Himling Center for Robotics Surgery at Imperial College London, founder and editor-in-chief of Science Robotics, chairman of the British Association of Robots and Automatic Control Systems, and was a member of the World Economic Forum's Global Agenda for Artificial Intelligence and Robots. Professor Yang was awarded a Commander of British Empire and honored as a Fellow of Royal Society of Engineering, a Fellow of IEEE Society, a Fellow of UK Institution of Engineering and Technology, a Fellow of American Institute of Medical and Biological Engineering, a Fellow of Medical Imaging, Image Computing and Computer-Assisted Interventions, and he's also a recipient of the Royal Society Research Merit Award and listed in the Times Eureka Top 100 in British Science. He is hired as a visiting professor of Shanghai Jiao Tong University and served as the founding dean of the Institute of Medical Robotics. And currently he is appointed as full-time as the chair professor of Shanghai Jiao Tong University. Professor Yang's main research interests are in medical imaging, sensing, and robotics. In imaging, he is credited for a number of novel MR phase contrast velocity imaging and computational modeling techniques that have transformed in vivo blood flow quantification and visualization. These include the development of locally focused combined with real-time navigator echoes for resolving respiratory motion for high-resolution coronary angiography. as well as MR dynamic flow pressure mapping, for which represents a paradigm shift of learning and knowledge acquisition of motor and perceptual and cognitive behavior of robotics, as well as the field of body sensor network, for providing personalized wireless monitoring platforms that are persuasive, intelligent, and context aware. He has published over 300 peer-reviewed publications, edited over 10 books and conference proceedings, numerous research best paper awards, and a large research grant portfolio from the UK and EU funding body, and he's as well as from research charities and industrial sources. So without further ado, let's welcome Professor Yang to deliver his speech. Okay, Professor Yang, are you able to unmute?
Hi, so can you allow me to, can you hear me? Let me to share my screen?
You should be able to go ahead and share your screen. Yes.
Okay, can you all see my screen? Right.
Yes, great.
Wonderful. So first of all, thank you very much for the kind introduction, and I'm delighted to speak here. So I'm going to talk about robots and probably give an overview of what's the current state of art and also where it is moving towards in future. So I'm the editor for Science Robotics. So for today's talk, I'm going to cover all different aspects of robots, but also try to spend a little bit more time talk about medical robots, which is my own research area. So when we talk about robots that, you probably have seen many of them that in fact, that during this COVID-19 outbreak, that we start to really realize the importance of robots when you have, want to impose social distancing. And in fact, that when I was isolated in a hotel room in Shanghai, that, for a few days, my food was delivered to me by a little robot, managed to go up the stairs, or go up the lift, and also to my door and give my food. Therefore, there's no human contact. Certainly when you go to factories and so on, so for instance, for car manufacturing, and you see many of those robots around that, in fact, that when you go to a car manufacturing, such as BMW or Mercedes, that you'll probably see more robots than the human workers on the plant. And the robots are developed for working in dull, dirty, dangerous environments, and this is what they are there for. So, from the mechanical accuracy, repeatability, and many things that, the accuracy that demands high precision, and the robots can certainly do a better job in many cases. So robots also take a different form, that the drones are the example that you probably have used this type of drone that for as a hobby, and also that some of you may have already using this robots for cleaning in a home environment. Autonomous cars certainly is an example of those robots, and robots are used for, understandably, that for space exploration, Mars mission, and also they are used in hospitals, hospital automation, for instance, in pharmacies. That those jobs are certainly repetitive and requires high precision. You can imagine the impact of giving the wrong drug to the wrong person, and certain drugs that, such as those using chemotherapy, that they are, they are harmful. So the use of robots certainly makes a perfect sense. And robots are used in construction. That construction, in this case, that they use this for combined with additive manufacturing, so you can generate this highly complex structure that by the use of new materials. So 3 years ago, that me and Marshall McNutt, that who was the then editing chief for Science, and we put together this new journal called Science Robotics. And the idea here is really to think ahead what the robots might be in the next 10, 20 years. So will robots still be in the form of gears and the motors, or there'll be fundamental changes, shifts that in the construction of robots? And the robots that perhaps by using new materials, the robots can combine sensing, actuation, and also that can be combined with certain level of computation. What about the powers that Professor Zhongling Wang just gave you a very nice lecture about the use of his nano generator that for generating power that without the use of batteries. And certainly that, when you want to deploy robots in a different kind of environments, power become an issue. So over the last 3.5 years that, we have published a diverse range of robots, but the underlying theme is very clear. It's science for robotics and robotics for science. So science for robotics is really to look at changes or advances in basic science, how this will reshape the future of robots. Robots will take different forms that, I will give you some examples later on. And robots for science, that how robots will be used to advance the development or providing insights into our understanding of science. And in fact, that many of you probably that, like me, are frustrated that laboratories are not fully open. Imagine one day that, for wet labs that we have robots that are performing those experiments for you, and you can intervene, examine, and also perform complex, experiments remotely from home or remotely from a different country. And by, also allowing international collaboration and so on, the future of science will be very different. So certainly that COVID-19 has introduced a lot of setbacks in our daily lives and also in our own research, but also that allowed us to rethink what the future may lie. In fact, a couple of months ago that we published this editorial that, on the use of robots for situations such as this, and perhaps that you can join us by thinking through some of the additional areas that we haven't thought about before. So let me just give you some examples of those robots we have published so far, and also that, how the motto of science robotics that, really mean, what do you mean by science for robotics, and what do you mean by robots for science? So this was one of the first papers that we published that, this is by the group in Berkeley University. And this robot on the left is called Salto. And basically it's trying to learn this little creature here, that this little creature here is called the bush baby or galago. And it is, apart from this very cute looking creature that it has some interesting features that, it's about 7 to 8 inches high and about only 5 to 10 ounces, but its tail is much longer than the combined length of the head and the body. And really that it is used to assist the animal's strong legs to power its jump. So the aim here is to learn from, this little bush baby and to learn how to jump as efficiently and also how to modulate the power during jumping. So this is an example that, how we can learn from nature and also how to construct better robots. So this is the work by Duncan Helden, who was working in Ron Fielding's lab in UC Berkeley. So if you look at this figure here, that the horizontal axis is the jumping frequency, and the vertical axis is the height gain. And if you look at this, that the black line is the ballistic limit that you can't go through that for obvious reasons. And Galago, which is located here, is really that in terms of height, as you can see, extremely efficient compared to bullfrog, that which is located here, which itself is extremely powerful in terms of jumping. And this is a mouse lemur, and you can see, probably find some of the other creatures. And those gray ones are those different robots that by different universities, the groups they have constructed over the years. So for instance, MIT Cheetah and so on. And the work that is reported here is somewhere located here. As you can see, it's getting close to what the Galago does. But put this aside, let's look at how it actually is doing. And you can see here that, how it is jumping and how it actually modulates power. And as you can see here. So this is one feature of that, what we try to do is, really to in this case, that how to learn from nature or provide bio-inspired mechanisms to provide better construction of robots. Here is another example, this by the work by Seth Hutchinson and his group in UIUC. And here is to provide a biomimetic robot to study the flight specialization of bats. As we know, bats are incredibly efficient in terms of gliding through the air, and also that, it's almost, in complete silence, and uses ultrasound to locate its prey. And in terms of aerodynamics, navigation, and all these things are really, surpassing any robot that we can construct so far. So what's special about this work? That is really a efficient use or efficient combination of material science. In this case, they use embedded carbon fibers that for the silicon membrane, and also incorporated those Hall effect encoders for the joints, that for the IMUs to give you the static and also dynamic acceleration, that also data storage on board with onboard control. So this is the construction of the robots, as you can see here, that extremely agile, and it provides the degrees of freedom, multiple degrees of freedom in terms of abduction, fraction, extension, retraction, protraction that's required to do it. And what is useful, that, or what is laudable for this work, is that they managed to put onboard processing and all these things online. And this is the general trend, is that robots, tethered robots, or what we called, that offload data, process on the computer, and also that it gets the power from the tether. It's useful to demonstrate some principles, but when you really try to deploy it for real life applications, that then it is limited. So increasingly we are trying to combine all this on board. Then you can imagine the type of constraints we will have. Number one is the computation. You have limited computation, limited data storage, limited wireless bandwidth. And as in the last talk, that you have limited power. So how do you get power from the environment, or harvest the power from the environment? And or how do you make effective use of the power on board and making all the processes low power? And these are all become major challenges. But that doesn't say that we have to ditch all our traditional, robotics or mechanisms that we learn in mechanical engineering. In fact, here's one example that by the work by Robert Wood in his group that in Harvard. As you can see here, that they use a rotary actually folding polyhydrogen and for midwater investigation of delicate marine organisms. As you know, that when you try to handle marine organisms in deep sea, they're extremely delicate. And certainly that you do not want to take them out of the depths onto surface, because pressure, everything changes. And this is, you can't observe them in the natural environment. So here, what they have put together is a very, a simple yet elegant folding mechanism that can be under-actuated. So it doesn't really have many degrees of freedom, but therefore it is easy to use, and that it can be deployed. As you can see here, that CS in action, deep sea down to 563 meters in the ocean. And you can see here how it actually moves and also captures very simple, elegant, and combines the beauty of traditional mechanism design with some, in this case, the 3D printing and also so on. So this is another example that of using robots actually to help the marine scientists that to study their little creature in the sea. So robots comes in different sizes and forms. That this perhaps is one of the largest robot we have ever published. This is the work by MIT group that they use what we call the digital architecture. So in the old days, or in the current form, prefab on bricks and so on, they are very useful. But imagine when you go to an environment that, an environment in a remote location that where you don't have such, and you'll be able to harvest local material, in this case, that, to construct such buildings, digital architecture. And when you try to one day, perhaps that when we try to, put inhabitants on the Mars, that certainly you can't send bricks up there. So that, this type of digital architecture becomes highly interesting. So here the challenge here is that when you have a large span, in this case, they use a crane that, to hold this base robot. And this in the robotic world is really the macro mini system. How do you ensure to have the accuracy and also this as well as the span for the, robot actuation, and in this case for making this very intricate architecture. And here there's also the material science elements to it. So as you can see that, all this are really changing the way we do science, changing the way we do engineering, and in many different ways. So those really open the doors for many architectures which would be difficult to construct in our traditional means. Then there are other examples that you can make use of robots that or construct robots. And this is the work that, to look at David Hu and his group that to look at origami. You are all familiar with origami, that in folding the papers. Here that is about cutting the papers to actually construct a soft robot that emulate the skin, in this case, of the reptiles. So they investigated different patterns and how this can be used. And this robot is completely driven by air, that therefore is in the area of soft robotics, that which is also a very popular field in a sub-branch of robotics, and they are used for a number of different applications. A few more examples that, when you want to explore the complex spaces that, whether in the through the cracks that, or even inside the human body, that what we call the endoscopes. And traditionally that you try to push something into those gaps, but how about we can have something that can grow from its tip, and therefore you don't need to push, and you allow it to navigate a very complex environment. You can also sense, from the tip. So here's one example. You learn from nature that how the neuron grows, how the pollen tubes grow, and also that how the plant cells grow. And this is the work by Alison Akamura in Stanford University that in this case is called the Eversion robot. Basically, it consists of folded up balloon that inside, but then when you press the air, that it actually extends itself. So therefore that it can manage situation like this. And some of the more tricky ones that you may encounter in surveillance or search and rescue, as well as that for that inspection and some of the hostile environments. And it can even go through this very narrow gaps. So certainly that, this is very simple. The material doesn't take much to put together, but it's a kind of new thoughts that you can put into it. But you may think this is just a gimmick and it's a bit of a fun, but there is, this, a significant in-depth simulation and also knowledge behind this if you want to do this accurately. And when you want to combine this for navigating the complex environment, how do you actually model this? How do you use visual surveying to locate your target and all these things actually that are not easy to do. And therefore, from this, you can distill basic science elements and to help you to understand and also to pursue. So it becomes clear that the development of future robots, that you need to really think out of the box. And also you need to think about different ways of navigating this complex environment. You need to learn from the nature. But in terms of constructing materials, learn from Mother Nature, perhaps that's another example here that for those of you who are working in material science, and you probably have studied this, the gecko's feet and how it actually manages near horizontal or near vertical walls, and also that, be able to walk upside down on the ceiling. So if you look at this, the microstructure of the gecko feet after this lecture, that you'll be, interesting to look at it. And these are effectively dry sucking pads. And by using this gecko-inspired construction, then you will be able to actually do this, dry, what we call the dry adhesives. And in this case, to help grasping and also manipulating large objects in microgravity, i.e. in space, that, on different planets. So these are some examples that, how bio-inspired design, how new materials and also the intersection between other disciplines can help the development of new robots. But for many of you who are outside of robotic field, perhaps that, influenced by Hollywood films, that robots needs to take a human form, that, what we call the humanoids. And traditionally, that the humanoids, the robots, that you may have seen them in films and also in DARPA challenges and so on, they look like clunky machines. So, certainly that they certainly look like being machined, and there are a lot of motors and gears, and they look clunky and also not really agile in the way that we wish them to see. But things are changing, that, that there are soft, what we call the soft muscles that can be used to help to construct the new ways of actuation. So this is the work by Professor Inaba from Tokyo University on human mimetic style humanoids. So without going through the detail, here's the video that demonstrating that how it actually works. So here that, the pneumatic muscle that, really to help with in terms of with the, the flexion, and the robot itself is quite, strong, yet you don't, look at, it doesn't look being formidable or frightening. And it can do so this push-ups and various things. And certainly that can do some interesting things that you would expect them to do to interact. Getting the gait cycles, the foot, being able to turn, being able to recover from falling. And all these are simple things for us, but for robots still nowadays are difficult. So perhaps this is one direction that we can move towards in the future of robots. So you put this aside, to put all this together, what about intelligence? That, how do we learn from this? So, I mean, deep learning and all these things are, deep learning, these are all deep learning, and these are all, interesting fields, and in robots grasping, objects, and also that to be able to play games that in this case, this game is certainly not easy to play, but by the use of robots, and also that to learn from those skills, explore this unknown environment, and these are interesting things that we are working towards. So this is really that it's timely that perhaps to look at some of the grand challenges, the challenges in robotics. So certainly from what I just described, that if we want to really move beyond the traditional means of motors and gears, we need to look at the new materials, and we need to look at the new fabrication schemes. And also that what about combining synthetic material with tissue material, or what we call the biohybrid materials? And what about learning from Mother Nature, so bio-inspired designs? So biohybrid and bio-inspired robots are very much, important development field. Power and energy, that the last lecture talked about the possibilities of new way of acquiring power, that certainly, as we know that, power and energy are very challenging things still that for any of the mobile devices. Robot swarms, how about the robots working together, that, the drones working together, but also that in the micro nano scales, those robots working together for targeting disease tissue and also be able to deliver therapy. What about navigation exploration that, go beyond the traditional SLAM approach, that simultaneous localization and mapping, that you have to map the environment and do, manage or navigate the environment? What about, going in unexplored areas and be able to know that where to look. Certainly that, as we human go to any building, we don't map it, we don't look at the map, that, we can build this environment from our, vision and also exploration and also prior knowledge. What about AI for robots? Will the traditional AI be sufficient, that, or there are new ways of doing it? What about explainable AIs, those black box approach of deep learning that, how do you ensure robots, in this case, all need to interact with a human, that they are safe, that they're explainable, their action, and so on. Brain-computer interfaces. That, brain computer interface is very important. That do we always need to use electrodes, optodes, that, or even implant, that like Elon Musk has done, that, into the brain in order to interact, or that we can use other means, surrogate measures to provide brain-computer interfaces. Social interaction, as robots become more popular in the home environments, what are the social, implications? That how do we make sure robots can really understand the subtlety of human interaction and human-robot interaction? Ethics, security, privacy, these are important issues, but certainly in future, in this very difficult time of COVID-19, perhaps it's also timely to talk about medical robotics, as that, not only they can be used for surgery, but also can be used for assistive tasks and also for managing patients in intensive care, those patients with infectious diseases. So medical robotics is my own area of research that for the last 2-3 decades. And as you know, robots in surgery is perhaps one of the first, ones that established its application. We all know surgery that, it's been done in open surgery, but in the 1980s, that they are largely done through keyhole surgery. The reason for that is you only need to make small incisions, and therefore that avoids major trauma for accessing to the disease part, and also make the recovery much, much quicker. Surgical robots is very much a novelty up to now, and in the last few years, it has enjoyed a tremendous growth because its safety, consistency, robustness, and as well as performing tasks that are difficult to be performed by bare hands. In future, that it certainly will have even more important role that how it's being used. So if you look at robots, that what we call that, it has gone through approximately 4 generations. The first generation, that these are robots just by adapting industrial robots, that thinking about the human surgery is like a CNC machining task, but certainly that's not the case. Then immediately that the research community and also industry, they're thinking that we need to develop this dedicated robots that are safe to be used in the surgical environment. So here are the generation of Zeus robot and also Da Vinci robot emerged in the field. These are the 2nd generation robots. And the 3rd generation robots are becoming smaller, and also they are designed for specializing to specific surgical tasks, and therefore that for spinal, for others. Then more recently, these are the 4th generation robots. They are a lot more sophisticated, that they combine with sensing, image guidance, and so on. But the future, the 5th generation robots are the ones that are really on the horizon, and I very much hope that, that the audience here, that you will contribute towards. First of all, that, unlike the previous generation robots, they are designed for dealing with late stage diseases. They are designed to deal with small lesions by the use of imaging and also other techniques that allow you to get to very deep-seated small lesions before it becomes causing irreversible damages. They are there to deal with complex diseases that are congenital, or those patients under major trauma, for instance, that, and therefore you allow you to do reconstruction surgery, microsurgery, and those things much better. And the future of robots will be implantable robots. As we get older, that we are going to lose certain capabilities, the robots will certainly will stay with us for longer periods when we go beyond the average age of 100 years old. So this one is one example of one of the latest generation robots called the Da Fengqi SP. It can use a single port, and it can be used for one small incision that with multiple instruments, then they're able to actually navigate those tasks and so on. So incisions are even getting smaller, and also that they can combine with imaging guidance, in this case for a case of removing part of the kidney called partial nephrectomy, and they provide augmented reality vision, tissue tracking, and also combined with imaging that to provide you with accurate margin definition and also accuracy. But things are getting even more, interesting. That what about dealing with smaller lesions that through the natural orifices? In this case, this is a robot system that developed by the Hamling Center by my team. That this is using Hyperflex bimanual control. As you can see here, those instruments are very small. They are all going through a single incision of only a few centimeters, and those instruments certainly provide the dexterity, and also that it's very, very different to what you see that in other on the market. So it can be used for the complex procedures, and also that for dealing with all the necessary steps. So if you look at all the different areas of robots, the areas enjoyed a lot of growth are laparoscopy, so that they are used, or what we call the keyhole up, surgery that through the body, the neuro ENT surgery, and the luminal surgery is one area that is emerging that through the natural orifices or that through the lumen, and also used in orthopedics. But as I mentioned, that the future is really to look at that early intervention and also dealing with diseases early. And I was talking about lung intervention, and certainly you will see those type of robots combined with vision. And in this case, when you try to miniaturize those robots to the size of 2 to 3 millimeters, then you need new fabrication schemes. And we are already that, having those type of robots, we're able to make those robots to the size of sub-millimeter, and therefore that to interrogate all this. So this is really one area that the new materials and the fabrication schemes will help. So if you look at the traditional area that those robots are, they're in the size of millimeter and beyond. But when you go down to sub-millimeter, then certainly you need microfabrication schemes to be able to construct those devices very, very small. So here is one example, the kind of limit you can do. So this is this grasper that the jaw to jaw is only 60 micron. So what's the size that to put into scale? The human head, the diameter is about 100 micron. So here, this combined with sensing actuation, and is only at the tip of your hair, you'll be able to put a couple of those graspers. So this is not a limit that if you are interested in following our work, this is our latest work published in Science Advances. That in this case, that using pneumatic piston actuation with a surface tension seal, and this is only that to the size of 120 micron or so, 150 micron or so. So, and with this, that it's just not much bigger than the hair, and therefore that you can see the actuation schemes that can provide. So the future, that development, certainly we are getting smaller, and the use of micro robots will become more and more available. That we are developing this new technology called the fiberbot, that and this then can be combined with the existing development of microrobotics that force delivery, surgery, sensing, detoxification, a number of different things. And then you can just combine it with chemical, magnetic, acoustic, and also biological propulsion. And with this, then a lot of the new things that can be done to deal with situations cannot be done before. So microrobotics will be an area that in development in future. They are micro scale in size, and they can be fabricated with micrometer scale accuracy, and they can also be manipulated of that, manipulation of micrometer scale objects. And all this, that if you put this together, that certainly that, linking medical robotics to the number of different topics we're talking about, new materials fabrication, biohybrid, bio-inspired robots, and the robot swarms, that how those micro robots work together. I didn't have time to discuss about navigation, BCI and those related to medical robotics. Perhaps that, you can follow on some of my other lectures that, I'll be delighted to talk about this. So as the chairperson just mentioned that, I actually made the decision that to move back to Shanghai last November, and to set up this new institute for medical robotics. So this perhaps is the largest dedicated medical robotics institute in the world. And we are involved in all the areas I mentioned about early on, and we have 10 different centers. And in fact, in early July, there is a robotics summer school. I think we are still taking applicants. If you are interested, that you can scan this QR code and to join us. So with this, I would just like to wrap up in this lecture talk. I mentioned, I very much give an overview, given the diverse background of the audience, of robotics and what do you mean by science for robotics and this robotics for science, and some of the challenges related to that. It's very much an overview talk. And if you are interested in some of the specific issues that I discuss here, that you're welcome to browse through the papers we publish on the journal, and also that to follow our WeChat page that for the SJTU Medical Robotics Institute. So I would like to thank the organizers for organizing this virtual conference. Look through some of the talks and also topics. They are extremely interesting, and delighted that, to have the opportunity to share with you our experience here. Thank you very much indeed. Thank you for your attention.
Thank you, Professor Yang, for your very extensive overview of the state-of-the-art robotics and detailed explanation of the medical robots. And due to the time constraint, we'll do 2 quick questions. So the first question we have in the chat is that, what is the biggest challenge?
So go back to the chairperson.
Yeah. Right, so we have the question in the chat that, what is the biggest challenge of the telesurgery for the medical robots, and what is the maximum distance to control the robot without losing transparency today?
Yeah, so there is no such thing, there are in fact many challenges for telesurgery. I think in addition to the accuracy, flexibility, learning, and all this I mentioned, and for telesurgery, one of the things is related to communication, which I didn't mention or elaborate today. So latency is a big thing. So when you have, hand-eye coordination, that when the vision and the motor, that there is a more than 100 millisecond delay, then you can noticeably feel it. So this, lag will become an issue that when you do that. But here that, not so much the distance, the physical distance, is rather the latency that really matters. So imagine that when we want to do surgery or control a robot on the International Space Station, or that, let's say, one day on the Mars, then such delay will become really a problem. So we wrote a paper, that editorial, on different levels of autonomy. So you can imagine that, in such situations, certain levels of autonomy that will need to be incorporated. So this very much the surgeon tell the robot what to do, but the exact details dealing with the exact steps, that and so on, navigating, dealing with the local tissue and so on, that will be done autonomously. So that will be the combination of both that will need to be used to handle such latency. So it's not the physical distance, And it's the latency that really matters, that to ensure that we don't lose the transparency. I suppose that's what you mean.
Okay, thank you, Professor Yang. Do we have any further questions? Okay, I'll have a quick one. So, Professor Yang, what is the current regulation on medical robots, and how does that affect the development of it?
Yeah, so medical robots that, currently there are no specific regulations for medical robots. They are really, the standards and all these things are, being put together because the field itself is relatively new. However, that we generally follow through the medical devices directive, so that, all surgical robots, they are regarded as class 3 medical devices. Therefore, they need to go through stringent testing and regulatory approval and all the necessary steps as those devices used for patients. So if you are interested in joining this as a startup company, then you need to be patient. That it takes a long time to get a device from concept to prototypes to the market.
Okay, I think that should wrap up the keynote speech of today. And thank you very much, Professor Yang, for joining us. And I hope we can see you again in the near future events.
Delighted to be here. Thank you very much and enjoy your day. Thank you.
Okay, that ends our keynote speeches of today, and we will proceed to the afternoon symposiums. And I'll have the details posted